Hello there, and welcome to Sleepy Science Vault. Settle in. Take a slow, deep breath, and let yourself become still. Tonight, we're going to explore something extraordinary. Something that sits at the very heart of how the universe works. We're going to talk about light, and why nothing in existence can ever travel faster than it. Take another slow breath. Let your body sink into wherever you're resting. And just listen. You've probably thrown something before. A ball, a paper airplane, maybe just a set of keys across the room. And without even thinking about it, you understood that the harder you throw something, the faster it goes. That's just how the world feels. Push harder, go faster. It seems so obvious, so natural. But here's where something beautiful happens. Because the universe has a secret. A quiet, profound secret. There's one thing that completely breaks that rule. Light does not care how hard you push. Light travels at exactly 299,792,458 meters per second. Every single time. No more. No less. That number is not an estimate. It is not approximate. It is fixed. It is woven into the fabric of everything that exists. Scientists call it invariant, which is just a gentle way of saying it never, ever changes. Let that sink in for a moment. No matter where you are in the universe, no matter how fast you yourself are moving, if you measure the speed of light, you will always get the same answer. That is deeply strange and deeply beautiful. In the early 1900s, a young man named Albert Einstein sat quietly with a question that had troubled him for years. What would it feel like to ride alongside a beam of light? He wondered. He imagined. He thought slowly and carefully. And from that stillness came one of the greatest ideas in human history. He proposed something called the special theory of relativity. And at its very center were two quiet postulates, two foundational truths. The first was simple. The laws of physics are the same for everyone, everywhere. Whether you are standing still or moving smoothly through space, the universe plays by the same rules. For all of us. The second postulate was stranger, and somehow even more calming. The speed of light in empty space is always the same. No matter who measures it. No matter where they are. No matter how fast they're moving. The answer is always the same. Think about what that means. If you were on a spaceship, traveling at half the speed of light, and you shone a torch out in front of you, you might expect that light to travel at 1.5 times its normal speed. That's what common sense would say. But common sense is gently, quietly wrong. The light would still travel at exactly the speed of light. Nothing added. Nothing taken away. Just the same. This isn't just true for torches on spaceships. It is true for every signal, every flash, every ripple of light across the entire universe. Radio waves from distant galaxies, starlight from suns that no longer exist, the gentle glow of a lamp in a quiet room. All of them travel at the same speed. Let your breathing slow a little more. There's no rush here. Just soft facts, drifting past you like clouds. The speed of light is not just fast. It is a constant, a universal constant, one of a small number of numbers that appear to be built into the universe itself. Scientists write it simply as the letter C. Small, elegant, precise. It appears in equations across all of physics, from the smallest particles to the largest structures in the cosmos. It is everywhere. And here is something quietly profound. The speed of light is not just a speed limit imposed from the outside. It isn't like a road sign that someone put up. It emerges naturally from the mathematics of electricity and magnetism. In the 1800s, a brilliant Scottish physicist named James Clerk Maxwell wrote down a set of equations describing how electric and magnetic fields behave. And when he solved those equations, something fell out. A speed. The speed at which electromagnetic waves travel. And that speed matched the speed of light. Exactly. Maxwell didn't set out to discover this. He was just following the mathematics. Quietly, carefully. And the universe whispered back to him, "Here is my speed. Here is how fast light moves." This tells us something remarkable. The speed of light isn't arbitrary. It isn't random. It arises from the deep geometry of space and time themselves. Some physicists describe it as the speed of causality, the speed at which any influence can travel, the speed at which one thing can affect another. Picture space and time, not as two separate things, but as a single, unified fabric. A four-dimensional tapestry that wraps around everything that exists. And woven into that tapestry is a limit, a gentle but absolute limit, on how fast anything can move through it. That limit is c, the speed of light. There is something else. Something quietly mathematical that tells us why this limit exists. When physicists describe motion through spacetime, they find that every object moves through the combined dimensions of space and time at exactly the speed of light. Always. When you are perfectly still, all of that motion flows through time. You are hurtling through time at the speed of light. Right now. As you rest. As you breathe. As you slowly drift toward sleep. But when something moves through space, some of that motion is redirected, taken away from its journey through time. And light, which moves through space at the maximum possible speed, moves through time. Not at all. For light, time does not pass. Let that be something you carry gently into sleep tonight. Light, traveling across the universe, arriving at your eyes from stars millions of light years away, experiences no time at all. For the photon, departure and arrival are the same moment, and perhaps that's why this speed limit exists. Not as a restriction, but as a kind of completion, a wholeness, a boundary beyond which the mathematics simply falls quiet. When physicists look at what would happen if something tried to exceed the speed of light, they find that the equations begin to ask impossible questions. What is the square root of a negative number in physical space? What does it mean for time to flow backwards? The concepts themselves gently break down. There is no faster, because faster has no meaning beyond this point. It is not that something is stopping you from going faster. It is that the word itself, the idea itself, ceases to correspond to anything real. And yet, from a certain angle, this is not a sad thing. It is a peaceful one. The universe is not infinite in every direction. There are edges, gentle ones, built into the very nature of space and time. And one of those edges is c, the speed of light, constant, calm, and quietly holding everything together. Let your thoughts drift now, like light moving through the dark, patient, unhurried, traveling at the only speed the universe allows. You don't need to hold on to any of these ideas. Just let them pass through you, softly, slowly, the way light passes through a still and quiet room. Rest now. There are more facts to come, gentle and slow. But for now, just breathe and let the universe hold you exactly where you are. Still here. Good. Let your body settle a little deeper. Let the weight of the day drift a little further away. We're going to continue our slow journey through one of the most quietly astonishing ideas the universe has ever revealed to us. Take a gentle breath and follow along. So far, we've established something simple and something profound. Light moves at the same speed for everyone, always. But now, something extraordinary begins to happen. Because if the speed of light is fixed, if nothing can change it, then something else must bend instead. And what bends is far more personal than you might expect. What bends is time itself. Imagine two clocks, perfectly synchronized, perfectly identical. You keep one, and you send the other on a very fast journey, perhaps aboard a spaceship, moving at a significant fraction of the speed of light. When the spaceship returns, and you compare the two clocks, they no longer agree. The clock that traveled has ticked fewer times. It has experienced less time. This is not a malfunction. This is not an error. This is the universe working exactly as it should. It is called time dilation, and it has been measured, confirmed, tested, not just with spaceships and thought experiments, but with real atomic clocks, flown on real aircraft. The difference is tiny at the speeds we experience in daily life. But it is real. Unmistakably. Quietly. Real. Let that rest with you for a moment. Time is not the same for everyone. It never was. We simply move too slowly in our daily lives to ever notice. And it isn't only time that changes. Space changes too. If you could observe something moving past you at an enormous fraction of the speed of light, it would appear compressed, shortened, squeezed along the direction of motion. A long spacecraft, hurtling past at near light speed, would appear to you shorter than it truly is. This is called length contraction. And like time dilation, it is not an illusion. It is not a trick of perception. It is the geometry of the universe, responding to motion, bending space, the way a gentle hand bends a piece of cloth. Both of these effects, time dilation and length contraction, point to the same quiet truth. Space and time are not rigid. They are not fixed. They flex. They shift. They breathe in response to how things move through them. Now, here is something that might seem like a contradiction, but is actually one of the most beautiful ideas in all of physics. If you were the one moving at near light speed, you would not feel anything strange. You would feel perfectly still. The universe around you would look compressed. Time outside your window would seem to be moving differently. But you, in your own experience, would feel completely normal. This is because there is no special reference frame. No fixed point in the universe that gets to say, I am truly still. And everything else is moving. Every observer, no matter how fast they travel, is equally valid, equally real, equally at rest, from their own perspective. Einstein understood this deeply. He called it the principle of relativity. And it means that the universe has no center, no throne, no privileged place from which all motion is judged. We are all equally at rest in our own quiet corner of space-time. Let your breath slow even further now. There is something almost meditative in that idea. No one perspective is more real than another. Every observer carries their own slice of time, their own measure of space, their own private experience of a shared and infinite universe. We spoke earlier about space-time, that unified fabric of 4 dimensions, 3 of space, and 1 of time. And we said that everything moves through it at the speed of light. Always. When you are still, all your motion goes into time. When you move through space, some of that motion is borrowed from time. And this exchange, this gentle trade between space and time, follows a precise and beautiful rule. Think of it as a kind of exchange rate between space and time. Not arbitrary, not rough, but exact, governed by the speed of light. Every meter you travel through space costs a precise amount of your journey through time. And the faster you move through space, the slower your clock ticks. The shorter distances appear, the more space-time reshapes itself around you. And there is a boundary on this exchange, a hard and gentle limit, called the time-like bound. When physicists describe intervals in space-time, the gap between two events, a flash of light here, a footstep there, they can calculate something called the space-time interval, a kind of distance that combines both space and time together. For objects with mass, like you, like stars, like planets, this interval is always time-like. It always has more time in it than space. It always points forward through time. Light is different. Light lives on the boundary. The space-time interval for a beam of light is exactly zero. Not small. Not almost zero. Zero. For light, departure and arrival are separated by neither space nor time. In the deepest geometric sense, they are the same event, folded together, touching. Rest with that for a moment. The universe has a shape, and light travels along the very edge of that shape, the boundary between what is possible and what simply is not. In physics, this boundary has a name. It is called the light cone. Imagine yourself at a single point in space and time. Right here. Right now. From that point, the future spreads outward, like an opening cone of possibility. Everything you could ever reach, everything that could ever reach you, everything that could ever be influenced by this moment, lies inside that cone, defined by how far light could travel from here in a given amount of time. Outside the cone, events are beyond your reach. Not just practically, not just because you're too slow, but fundamentally, causally, forever. No signal, no influence, no message of any kind could ever connect you to what lies outside your light cone. And the walls of that cone, the very boundary between what is reachable and what is not, are defined by the speed of light. See. Always see. Nothing crosses those walls. Nothing ever has. This might sound isolating, but there is something peaceful about it too. A kind of cosmic privacy. A quiet sphere of influence that belongs only to you. Shaped by the light you've sent out, and the light that has reached you. A universe of connection. bounded gently by the speed of light. Let that thought drift through you softly. Your past, your present, your future, all held inside a cone of light. Warm, finite, yours. Now, one more gentle idea before we move on. Something that ties all of this together. When Einstein laid out his theory of relativity, he was careful about something that many scientists before him had overlooked. He insisted that the laws of physics must produce the same results for every observer, regardless of how they are moving. This seems obvious when you say it quietly. Of course, physics works the same for everyone. But the implications are staggering. Because it means that there is no experiment you can do, no measurement you can make, no observation that will reveal some absolute, true, universal state of rest. Reality is observer independent. In the deepest sense, the speed of light is real for everyone. The laws are real for everyone. But the specific measurements of time and space, length and duration, those are personal, private, different for every observer, and equally valid for all. The universe does not have one true clock. It has infinitely many. All of them correct. All of them ticking at their own quiet rate. Breathe slowly now. We are moving into something new. Something that answers a question you may have already begun to ask. If space and time bend so dramatically at high speeds, what happens as something approaches the speed of light itself? Why can't it simply keep going and eventually reach it? Here is the gentle, unavoidable answer. Because of what you are made of. Every object that has ever existed in your experience. Every person. Every planet. Every grain of sand. Every breath of air has something called rest mass. Mass is a measure of how much matter something contains. How much it resists being pushed. How much gravity it responds to. And rest mass is the mass something has when it is simply sitting still. Light, a photon, a single packet of electromagnetic energy, has no rest mass. None at all. Zero. This is not a small thing. This is the entire reason light can travel at the speed it does. Only something with zero rest mass can travel at sea. Anything with even the tiniest amount of mass cannot. And here is where the mathematics becomes quietly beautiful and quietly absolute. As an object with mass moves faster, something strange happens to it. Its effective mass, the mass it appears to have from the perspective of the universe around it, begins to increase. Not by a little, by enormous amounts. As it approaches the speed of light, the equation that describes this is elegant and merciless. As speed increases toward c, the factor by which mass increases grows toward infinity. At half the speed of light, an object is a little heavier than at rest. At 90%. Significantly heavier. At 99%. Many times heavier. At 99.9. Heavier still. And as you reach ever closer to see, the mass approaches infinity. An infinite mass would require infinite energy to push. And there is no such thing as infinite energy. Not in our universe. Not anywhere. So the speed of light is not just a rule. It is not just a law written somewhere in a book of physics. It is a mathematical wall, built into the structure of mass and energy themselves. The closer you get to it, the harder the universe pushes back. Gently. Firmly. Absolutely. And so massive things. Things made of matter. Things like us can only ever approach the speed of light. Never reach it. Never cross it. Like a horizon. Always ahead of you. Always the same distance away. No matter how fast you travel toward it. There is something almost poetic about that. The speed of light. Unreachable. Not because the universe is cruel, but because the universe is consistent. Because the mathematics of mass and energy and spacetime are woven so tightly together that this limit emerges naturally, inevitably, quietly. And so we rest here for a moment, in the soft knowledge that you are made of mass, and mass belongs to the slower world, the world of planets and people, of breath and heartbeat, of long and gentle nights. You are not built for the speed of light. You are built for this, for stillness, for rest, for the slow and beautiful passage of time. Let your eyes grow heavy now. Let your thoughts become soft and unhurried, like starlight, traveling patiently across the dark, in no particular rush to arrive. There is more to come. More quiet facts. More gentle truths about light and the universe that holds it. But for now, just rest and let the darkness carry you slowly and without effort forward through time. Still with me. Good. Let yourself settle even deeper now. Let the quiet wrap around you, like something warm and familiar. We've been traveling together through some of the most profound ideas the human mind has ever uncovered. And tonight, we go a little further, a little slower, into the deep mathematics and deep philosophy of why nothing can travel faster than light. Take a long, slow breath and let it go. We ended last time with a gentle wall, a mathematical boundary built from the nature of mass itself. As something with mass moves faster, its effective mass grows. And as it approaches the speed of light, that mass grows toward infinity, which means the energy required to push it further also grows toward infinity. But let us sit with that word, infinity, for just a moment. In mathematics, infinity is not simply a very large number. It is not a number at all. It is a concept, a direction, a way of saying, there is no end to this. And when the energy required to accelerate something reaches infinity, it does not mean you need a very large rocket or a very powerful engine. It means the task itself becomes impossible. Not difficult, not expensive, impossible. In the same way that it is impossible to count to the last number, or to find the edge of an infinite plane, the universe does not have infinite energy to offer. No corner of it, no force within it, no process that has ever existed can supply what would be needed to push a massive object all the way to the speed of light. So the wall is not physical. It is mathematical. And mathematical walls do not bend. Let that sit softly in your mind. There are some things the universe simply cannot do, and this is one of them. Now, here is where something extraordinarily beautiful enters the picture. Something you have almost certainly heard before, but perhaps never quite felt in its full, quiet depth. E = mc squared. This is perhaps the most famous equation ever written. 5 symbols, carrying more meaning than entire libraries of words. What it tells us, in the gentlest possible terms, is that energy and mass are the same thing, not similar, not related, the same, two faces of a single coin. Mass is frozen energy. Energy is liberated mass. And the exchange rate between them is c squared. The speed of light multiplied by itself. An almost incomprehensibly large number. This is why even a tiny amount of mass contains an enormous amount of energy. And it is also why, as something accelerates toward the speed of light, the energy you pour into it does not simply make it faster. It makes it heavier, more massive, more resistant to further acceleration. The energy transforms into mass rather than speed. The universe takes everything you give and quietly converts it into more resistance, more weight, more wall. It is as though the universe is saying, gently, patiently, you cannot get there from here. No matter how much you give. Breathe slowly. This equivalence of energy and mass is not just a curious fact. It is the mathematical core of the proof that light speed cannot be reached. When physicists write down the equations of special relativity and follow them carefully, step by step, with no assumptions, no shortcuts, the conclusion emerges on its own, not as something imposed, but as something discovered. The mathematics itself arrives at a quiet, absolute answer. A massive object requires infinite energy to reach C. And since infinite energy does not exist, the speed of light remains forever, just beyond reach. There is something almost meditative about a mathematical proof. It asks nothing of you. It does not require belief, or faith, or trust. It simply follows, one step at a time, until the truth is unavoidable. And the truth here is unavoidable. The speed of light is the speed limit of the universe, not by decree, but by necessity. Now let us think about something perhaps a little more intuitive. Speed, and how it adds up. In everyday life, if you are on a train moving at 100 kilometers per hour, and you throw a ball forward at 50 kilometers per hour, the ball moves at 150 kilometers per hour relative to the ground. Simple addition. Clean. Obvious. But at speeds approaching light, something different happens. Something quiet and strange. If you are moving at 80% of the speed of light, and you shine a torch forward, the light does not travel at 80% plus 100%. It does not travel at 180% of C. It travels at exactly C. As always. As it must. And if instead of a torch, you fired a particle forward at 80% of the speed of light relative to your ship, the particle would not be moving at 160% of C relative to an outside observer. Einstein derived a new rule for adding velocities, a rule that works at all speeds, not just slow ones. And this rule has a quiet but firm property. No matter what velocities you add together, no matter how cleverly you combine them, the result can never exceed the speed of light. You can add speeds together for as long as you like. You can stack them, combine them, layer them, and the universe will always give you back a number smaller than C, getting always closer, but never arriving, like a sum that approaches a limit, without ever quite reaching it. Forever. Asymptotic. Forever. Just shy. Let that image rest with you. An infinite sum, quietly approaching, a number it can never touch. Deep in the mathematics of relativity, there is a concept called full momentum. Do not worry about the details. Just let the idea drift past you, like a leaf on still water. In ordinary life, we describe momentum as mass times velocity. How heavy something is, multiplied by how fast it moves. In relativity, momentum must be extended into 4 dimensions, 3 dimensions of space, and 1 of time. Together, they form a single object, a 4-vector. called form momentum. And this form momentum has a fixed length, a magnitude, that never changes, no matter how fast something moves, no matter how you observe it. For a massive particle, this length is determined entirely by its rest mass. It is a constant, an unchanging signature of what the particle is. For a photon, a particle of light, the length of its form momentum is 0, which places it in a completely different category from anything with mass. The constraints of form momentum tell us something clear. Massive particles and massless particles are not simply different speeds of the same thing. They are different kinds of thing, living in different regions of space-time, governed by different rules, separated by a boundary that nothing can cross. That boundary is C. Here is something that might seem contradictory at first. A puzzle, a gentle paradox. As something with mass moves faster, its momentum increases. As it approaches the speed of light, its momentum approaches infinity. And yet, a photon, which moves at exactly the speed of light, does have momentum, real, measurable momentum, despite having no rest mass. How can something with no mass carry momentum? The answer lies in that same beautiful equation. E=mc², extended into its fuller form, which includes momentum as well as rest mass. For a photon, all of its energy is its momentum. There is no rest mass term, no stillness, no existence at rest. Only motion, only C, only a pure and elegant relationship between energy and movement. A photon cannot be still. For a photon, stillness does not exist. It was born moving at C. It will end moving at C. And in between, it does not experience time at all. There is something almost tender about that. A particle that can never stop, never rest, never slow down, always moving at the one speed the universe allows it. While you, right now, can rest, can be still, can let the universe carry you forward through time, without effort, without motion, simply breathing. Now, we come to something fundamental about space itself. When we say light travels at sea through a vacuum, we mean something precise. A vacuum is not simply empty space in the everyday sense. It is space with nothing in it. No air, no matter, no fields interfering, just pure, geometric space-time. And in that pure vacuum, C is the absolute maximum, not just for light, but for anything, any signal, any particle, any influence, any cause. When light travels through a medium, through glass, through water, through air, It slows down slightly. It interacts with the material it passes through, and its effective speed decreases. But this is not a violation of c, because c is specifically the speed limit of the vacuum. The interactions inside a medium slow the signal, but they do not allow anything to exceed c in vacuum. The vacuum is where physics is purest, where the rules are clearest, where c stands absolute, like a horizon that can never be crossed. Let your mind drift now to something very small. In quantum physics, there is a scale called the Compton wavelength, named for the physicist Arthur Compton, who probed the nature of light and matter. In the early 20th century, the Compton wavelength of a particle is the scale at which quantum effects become important, the scale at which a particle can no longer be treated as a simple point of matter moving through space, but must be treated as a quantum object, spread out, uncertain, wave-like. And here too, the speed of light appears. The Compton wavelength is defined using c, using the rest mass of the particle, and using the fundamental constants of quantum mechanics. It tells us something subtle. At scales smaller than the Compton wavelength, the nature of a particle becomes ambiguous. Pairs of particles can spontaneously appear and vanish again. Even in the quantum world, even at the very smallest scales of existence, c remains present, a constant, threading through every layer of physics, from the very large to the very small. It is not just a speed. It is a fundamental parameter of the universe itself. Breathe in slowly. And now, something that sounds almost like a story. A mechanism deep inside every particle that has mass, that is responsible for that mass existing at all. You may have heard of the Higgs field. It fills all of space, everywhere, like a vast and invisible ocean, rippling, present, fundamental. When particles move through this field, some of them interact with it. They experience a kind of gentle resistance, a drag, not in the everyday sense, but in the sense that they acquire inertia. They acquire mass. The stronger a particle interacts with the Higgs field, the more massive it is. The weaker, the lighter. Photons, particles of light, do not interact with the Higgs field at all, not even slightly, and so they have no mass. None. And because they have no mass, they must travel at sea. They cannot do otherwise. They have no choice. They have no rest state to return to, no stillness to settle into. The Higgs field is in some sense the origin of the difference between light and everything else, between C and the slower world of matter. The particles that make you up, electrons, quarks, the building blocks of atoms, All interact with the Higgs field. All acquire mass through it. And that mass is what keeps you here. Present. Warm. Slow. Beautifully. Impermanent. Let that feel like something quiet and profound. You are massive because of a field that fills all of space. And that mass is what makes you part of the slower, warmer, richer world. The world where time passes, where experience accumulates, where moments have weight. You could not experience anything if you moved at the speed of light. You could not think, or feel, or sleep. For you, time would not pass. Your mass is your ticket to this world. And the speed of light is the border beyond which this world does not exist. And now, finally, we arrive at perhaps the deepest reason of all, the most philosophical, the most quietly dramatic. Causality. Causality is the principle that causes come before effects. That a thing must happen before it can influence what comes after. That the past shapes the present, and the present shapes the future. In that order. Always. This seems obvious. Of course, causes come first. Of course. But in a universe where time bends, where different observers disagree about how much time has passed, there is a deep question hiding here. If something could travel faster than light, then for some observers, it would appear to travel backward in time. Not as a metaphor, not as a figure of speech, but literally, arriving before it departed, causing effects before the cause had occurred. This is not a paradox that can be resolved with clever thinking. It is not a puzzle with a solution. It is a fundamental breakdown of the structure of reality. If you could send a message faster than light, you could, under the rules of relativity, send a message into your own past. You could receive a reply before you sent the original. And from that point, logic itself begins to fray. Quietly, irrevocably. The universe appears to have noticed this. And the speed of light is the universe's quiet, firm answer. No. Causes come first. Effects come after. The arrow of time points only one way. And nothing is allowed to point the other way. This is called causality preservation. And it may be the deepest reason of all. Why the speed of light is what it is. Why it cannot be exceeded. Why the universe holds it absolute and still, at the center of everything. Not to limit us, not to keep us small, but to keep the universe coherent, logical, whole, so that causes lead to effects, so that memories point backward, and hopes point forward, so that the story of the universe makes sense, so that you can fall asleep tonight, knowing that tomorrow will come after today, gently, inevitably, as it always has. You are a creature of cause and effect, of memory and anticipation, of a universe that is ordered and quiet and moving always in one direction. Let that carry you now. The facts will continue. There is so much more to discover. So many more quiet truths, waiting patiently in the dark. But for now, let your breathing slow. Let your thoughts soften. Let the universe hold you exactly where you are. In this moment, that came after the last one, and before the next. Ordered, gentle, and completely yours. Sleep now, if you are ready. The speed of light will be waiting. When you return, patient, constant, and going nowhere. Still here, still with you. Take a long, slow breath, and let it out, even more slowly. We have been traveling together through some of the deepest ideas the universe has ever quietly offered. And tonight, we go deeper still. Not into complexity, not into difficulty, but into something even more fundamental. Something beneath the equations, beneath the mathematics, beneath even the physics. We are going to explore why the universe is the way it is, why it holds together, why it makes sense, why causes lead to effects, and why that will never, ever change. Settle into wherever you are resting. Let your shoulders drop. Let your breathing find its own quiet rhythm. And listen. The universe is consistent. This might sound like a simple thing, an obvious thing. Of course, the universe is consistent. What would an inconsistent universe even look like? But pause with that question for just a moment. What would it look like? It would look like a place where the same experiment, run twice, gave different results for no reason. Where water froze at one temperature today, and a completely different temperature tomorrow. Where light arrived before it left. Where effects preceded their causes. Where the rules changed. Without warning. Without pattern. Without mercy. That is not our universe. Our universe is logical. It is consistent. Profoundly. Beautifully. Consistently. Consistent. And the speed of light is one of the pillars of that consistency. If something could travel faster than light, the logical structure of the universe would begin to crack. Slowly at first, then all at once, like a pane of glass, struck in exactly the wrong place. So when physicists say that nothing can travel faster than light, they are not simply reporting a measurement. They are describing something deeper. They are describing the logical skeleton of reality itself. the framework that holds everything else in place. And that framework is consistent. Today, tomorrow, and in every corner of the universe. Forever. Let that feel like something solid beneath you. Like ground. Like certainty. In a universe full of mystery. Full of questions. Full of things we do not yet understand. This remains. The universe is consistent. And the speed of light helps keep it that way. Some physicists speak of this in a particular way. They describe c not merely as a speed limit, but as a cosmic safety mechanism. Imagine the universe as something extraordinarily delicate, a vast and intricate structure, where every part is connected to every other part, through the web of cause and effect, through the fabric of spacetime, through the flow of time itself. If anything could travel faster than light, that web would tear. Signals could arrive before they were sent. Effects could undo their causes. The past could be rewritten. The future could become the past. And the concept of now would lose all meaning. The speed of light prevents all of this. Quietly, firmly, without drama. It is the universe's way of protecting itself from paradox, from incoherence, from the unraveling of everything. Think of it as a kind of cosmic immune system, defending the structure of reality against the infection of logical contradiction. Every time a particle accelerates, every time energy flows, every time matter moves through space, the speed of light stands quietly at the boundary and says, "This far, and no further," and the universe remains whole. There is something deeply comforting in that. The universe is not fragile. It has a built-in protector, woven into the mathematics of spacetime itself. A guardian of logic, a keeper of coherence, an absolute and silent boundary, holding everything together. Breathe slowly. Now let us think about observers. You and I, and every being in the universe, experience reality from a particular point of view, a particular position in space, a particular moment in time, moving at a particular speed. And as we explored earlier, different observers can disagree about how much time has passed, about how long an object is, about the order of some events. But here is what they can never disagree about. They can never disagree about whether a cause preceded its effect. They can never disagree about whether a signal arrived after it was sent. They can never construct a story from their own frame of reference, in which the universe is logically incoherent. This is called observer frame consistency, and it is guaranteed by the speed of light. No matter how fast you are moving, no matter what angle you are observing from, no matter what your clock reads, or how compressed space appears to you, the laws of physics will look the same. Causes will precede effects. Light will travel at sea, and reality will make sense. Every observer gets a consistent universe. Not the same universe in every detail, but a coherent one. A logical one. One that hangs together and does not contradict itself. Let that feel like a gift. And behind observer frame consistency lies something even more fundamental. Something called absolute frame invariance. This is the idea that the laws of physics are not just consistent for observers moving at different speeds. They are consistent for observers in all states of motion. Accelerating, rotating, falling freely through a gravitational field. There is no preferred frame, no special vantage point from which the universe looks most true, or most real, or most correct. Reality is the same for everyone, everywhere, always. The specific numbers differ. The measurements change. But the laws, the deep underlying principles, remain invariant, untouched by motion, unbothered by speed, forever the same. And C sits at the heart of this invariance. It is the one quantity that every observer agrees on, regardless of how they are moving, regardless of what else they disagree about. They will always measure light moving at exactly C. In a universe of shifting perspectives, of personal time and private space, C is the one fixed point, the one shared truth, the thing that ties all observers together into a single, coherent, shared reality. Rest with that for a moment. You and a traveler crossing the galaxy at enormous speed would disagree about almost everything. About the length of ships, the ticking of clocks, the timing of distant events. But you would agree about the speed of light. In that one measurement, you are united. Across all the vastness, across all the difference, you share that number. C. Always C. Let that feel like something quietly beautiful. Now, something called the principle of locality. Locality is the idea that things are only directly affected by what is immediately next to them. A ball rolling across a floor is pushed by the floor beneath it. The floor is there, touching it, local to it. A flame warms your hand because the heat radiates outward through space, traveling from the flame to your skin, through the intervening distance, step by step, moment by moment. Locality means that influence must travel. It cannot simply leap across space without passing through the space in between. This principle is so deeply embedded in physics that its violation would feel almost violent, almost wrong, in a way that goes beyond mere surprise. And the speed of light is what enforces locality. If something could travel faster than light, influence could leap. Effects could appear at a distance. before anything had time to travel there. And locality, the quiet principle that the universe acts through contact, through proximity, through things touching other things, would collapse. This is sometimes called the ban on action at a distance. The universe does not allow things to reach out across space and affect something far away instantaneously, without a signal traveling between them. Gravity reaches across space, but it does so through the curvature of spacetime, a real physical effect that travels outward at the speed of light. Electromagnetism reaches across space through fields that propagate at the speed of light. Even the force between two magnets is mediated by photons, particles of light, carrying the influence from one to the other. At sea, nothing acts at a distance. Nothing bypasses the space in between. Everything travels, and everything travels no faster than light. Let your thoughts drift quietly with that. The universe is a place of contact, of propagation, of signals and carriers and mediators, traveling patiently through space, at the only speed that is allowed. In quantum field theory, the branch of physics that describes particles and forces at the smallest scales, there is a formal version of this principle called microcausality. Microcausality states that measurements made at 2 points in space that are separated by more distance than light could have traveled between them in the available time cannot influence each other. They are called space-like separated, outside each other's light cones, causally disconnected. And the mathematics of quantum field theory is constructed so that this is always respected. Always. At every scale. In every calculation. For every particle. For every field. Microcausality is not an afterthought. It is built into the foundations of how physicists describe the quantum world. Because even in the strange and probabilistic realm of quantum mechanics, even where particles tunnel through barriers and exist in superpositions and behave in ways that seem to defy common sense, causality is preserved. Information does not travel faster than light. Influences do not leap across space-like separations. The speed of light holds. Even there. Even in the quantum foam. At the very smallest scales of existence. Breathe in. And let it out slowly. Here is something you feel every day, but may never have connected to the speed of light. Time has a direction. The past is behind you. The future is ahead. Memories point one way. Anticipation points the other. You can remember yesterday, but you cannot remember tomorrow. You can influence what comes next, but you cannot influence what has already passed. This directionality of time, this arrow that points always from past to future, is called the thermodynamic arrow of time, and it arises from the fact that in large systems, Order tends to give way to disorder. Things spread out. Energies equalize. Complexity dissolves into simplicity. A broken cup does not reassemble itself. Smoke does not flow back into a candle. A ripple does not converge back to a central point. And this arrow, this one-way flow, is intimately connected to causality. And causality, as we have seen, is protected by the speed of light. If signals could travel faster than light, that arrow could be reversed. Information from the future could reach the past. The thermodynamic direction of time could become ambiguous, could become negotiable, could become meaningless. The speed of light holds the arrow in place. It ensures that time flows in one direction only, from cause to effect, from past to future, from the moment of your birth toward the long and quiet night of wherever you are going. Let that feel natural. Let that feel right. Time flows forward because the universe is consistent, because the speed of light holds firm, because causes come before effects, and always will. And now, something that may feel even more personal. Information. Everything you know. Everything you have ever learned. Every message you have ever sent or received. Every signal your brain has ever processed is information. Patterns. Differences. Distinctions that carry meaning. And information cannot travel faster than light. This is not simply a consequence of the speed limit. It is the speed limit in its most fundamental form. When physicists speak of c as the ultimate limit, what they really mean, at the deepest level, is that no information, no causal influence, no physical difference that matters to anything or anyone can propagate through space faster than light. You cannot send a message faster than light. Not by radio. Not by laser. Not by any quantum trick. Not by any mechanism that has ever been proposed, or ever will be. Some quantum phenomena seem to suggest otherwise. Quantum entanglement, for example, produces correlations between distant particles that seem almost instantaneous. But here is the quiet truth. No information is transmitted through entanglement. The correlations appear, but they cannot be used to send a message. They cannot carry meaning from one place to another. Faster than light. The universe is careful about this, precise about this. The mathematics always works out such that no usable information leaps the gap. Information is physical. It must be carried by something. A photon, an electron, a wave, a signal of some kind. And all of those carriers are bound by the same quiet rule. C. Always C. As the ceiling. Never exceeded. Never circumvented. The universe keeps its secrets. At the speed of light. No faster. And now, to bring this section to its gentle close, we arrive at something deeply mathematical, but quietly beautiful. Lorentz invariance. In the late 19th century, a Dutch physicist named Hendrik Lorentz developed a set of mathematical transformations describing how measurements of space and time change between observers moving at different speeds. These transformations, the Lorentz transformations, became the mathematical heart of special relativity. They describe precisely how time dilates, how lengths contract, how velocities combine, how energy and momentum transform when you shift from one frame of reference to another. And built into every one of these transformations, woven through every equation, central to every result, is c, the speed of light. Lorentz invariance is the principle that the laws of physics remain unchanged under these transformations, that the universe looks the same, sounds the same, behaves the same, no matter what speed you observe it from. It is one of the most tested principles in all of science, tested to extraordinary precision in particle accelerators, in atomic clocks, in measurements of cosmic rays, in observations of distant pulsars. And it has never, not once, been found to fail. Every experiment, every observation, every measurement confirms it. The universe is Lorentz invariant. The laws of physics do not depend on how fast you move. And at the heart of Lorentz invariance, always, is c, the fixed, the constant, the absolute speed of light. There is something profound in that constancy, in a universe that is in many ways endlessly relative, endlessly shifting, endlessly dependent on perspective. C stands alone, the one number that does not shift, the one measurement every observer shares, the one constant that threads through every transformation, every frame, every perspective, every corner of the cosmos. C. Let that number rest somewhere quiet inside you. 299,792,458 meters per second. The same for you and for a civilization on the other side of the galaxy, and for every observer who has ever existed or ever will. The universe agrees on very little. It lets time stretch, and space compress, and clocks fall out of step, and distances dissolve into different values, depending on where you stand. But it agrees on this, always, without exception, without compromise, without end. The speed of light is what the universe knows for certain. Let your breathing slow now. Let your body become heavy and still and warm You are a small and beautiful part of a vast, consistent, logical, luminous universe, held together by mathematics, protected by causality, bounded by sea. And tonight, you rest inside it, safe, still, moving gently forward through time, at exactly the speed the universe allows. More facts are coming, patient and soft, waiting for you in the dark. But for now, there is only this: the quiet, the stillness, the slow passage of a moment into the next. Sleep, if you are ready. The universe will hold, exactly as it always has. Consistent, constant, and completely at peace. Still here, still with you. Let the quiet settle around you, like something soft and familiar. Tonight we go somewhere few people ever travel. Not far in space, but deep in structure. Deep into the hidden architecture of the universe itself. We are going to spend some time inside the mathematics. Not to understand every detail, but to feel the shape of it. The way you might feel the shape of a vast building, simply by walking slowly through it. Noticing the height of the ceilings, the weight of the walls, the sense of something enormous and carefully constructed all around you. Take a slow breath and let yourself arrive fully. Here, physicists love symmetry, not just because it is beautiful, though it is profoundly, quietly beautiful, but because symmetry, in the mathematical sense, is one of the most powerful tools for understanding how the universe works. A symmetry, in physics, is a transformation you can perform that leaves something unchanged. Rotate a perfect sphere, and it looks the same. Reflect a snowflake along certain lines, and it looks the same. Shift an experiment forward in time by a day, and the laws of physics remain the same. These symmetries are not decorative. They are structural. Each one corresponds, through a deep and beautiful theorem, to a conserved quantity. Something the universe holds constant, no matter what happens. The symmetry of time translation gives us conservation of energy. The symmetry of space translation gives us conservation of momentum. The symmetry of rotation gives us conservation of angular momentum. And the symmetries of special relativity, the ones that include the speed of light at their very center, form a mathematical structure called the Lorentz group. A group, in mathematics, is a precise and beautiful thing, a collection of transformations that combine in consistent ways, that have a defined structure, governed by rules. The Lorentz group describes all the ways You can rotate and boost, move and transform through spacetime, while keeping the laws of physics intact. And c, the speed of light, is not a parameter that sits outside this group. It is built into it. It is the number around which the entire structure is organized. Change c, and the group changes. Change the group, and the symmetries change. Change the symmetries, and the conserved quantities change. And if the conserved quantities change, the universe as we know it simply does not exist. The speed of light is not just a speed. It is a cornerstone of the symmetry structure of reality itself. Let that feel like something large and quietly magnificent. Now, quantum field theory. This is the framework physicists use to describe the smallest things in existence. Particles, forces, fields that fill all of space, vibrating, fluctuating, giving rise to everything we can see and touch. Quantum field theory is extraordinarily successful. It is perhaps the most precisely tested, most thoroughly confirmed scientific framework ever developed. Its predictions match experiment to more decimal places than almost any other theory in history. And quantum field theory requires the speed of light in a way that goes beyond simple speed limits. To build a quantum field theory that is consistent, that does not produce nonsensical results, that does not predict infinite probabilities, or negative energies, or other mathematical absurdities. You must respect Lorentz invariance. You must build C into the foundations. Every field, every particle, every force, in a consistent quantum field theory, must transform correctly under the Lorentz group, must carry C within its equations, must respect the cosmic speed limit. At every scale, in every interaction. This is not an external constraint imposed upon the theory. It is an internal requirement, something the theory demands of itself in order to remain coherent. If you try to build a quantum field theory that violates Lorentz invariance, that allows signals faster than C, the theory begins to produce nonsense. Probabilities greater than 1. Negative probabilities. States with infinite negative energy. The mathematics rebels. Quietly, firmly, and falls apart. The universe, it seems, will not allow a consistent description of itself. That does not include C as an absolute limit. Breathe slowly. There is a property that physicists require of any good quantum theory called unitarity. Unitarity is a precise mathematical requirement. It says that the total probability of all possible outcomes of any quantum process must add up to exactly 1. This sounds obvious. Of course something must happen. Of course, the probabilities must sum to 1. But maintaining unitarity, in the face of all the strange and complex things that quantum fields do, is a deep and serious challenge. And one of the ways unitarity can fail is if the theory allows information or influence to travel faster than light. When causality is violated, when signals leap across space-like separations, the mathematical structure of quantum mechanics begins to lose its unitarity. Probabilities drift away from 1. Physical processes become undefined. The theory becomes unreliable. Unitarity is one of the reasons physicists take the speed limit so seriously, not just as an observed fact, but as a requirement of any theory that wants to describe a sensible and consistent universe. And our universe is sensible and consistent, and so it is unitary. And so, C holds. Let that feel like something solid beneath you. When physicists describe how particles and waves move through space, they use wave equations, mathematical descriptions of how disturbances propagate through fields, through spacetime, through the fabric of the universe. The solutions to these wave equations, the mathematical functions that satisfy them, describe waves that travel at particular speeds. And when you write down the wave equations for light, for gravity, for the fundamental fields of nature, and you solve them carefully, without assumption, something emerges. The speed c, not put in by hand, not assumed from the beginning, but derived from the structure of the equations themselves. Maxwell found this for electromagnetism in the 19th century. Einstein found this for spacetime in the 20th, and physicists have found it again and again in field after field, equation after equation. The universe's wave equations produce C naturally, inevitably, as the speed at which their solutions travel. The speed of light is not a measurement we impose on a reluctant universe. It is a number the universe derives for itself over and over again, in every equation, at every scale, in every theory. Rest with that. Gauge invariance. This is one of the most important and most beautiful principles in all of modern physics. A gauge symmetry is a special kind of symmetry where you can change something about your mathematical description locally at each point in space and time, independently, and the physics remains unchanged. The requirement that a theory be gauge invariant is extraordinarily powerful. It essentially forces the existence of forces. It demands that particles interact through the exchange of specific carrier particles, called gauge bosons. The photon, the particle of light, is a gauge boson. It exists because electromagnetism is gauge invariant, because the mathematics of charged particles demands a mediating field, and that field is light, and the photon, being a gauge boson, being the carrier of the electromagnetic force, must be massless. This is not a choice. It is a requirement of gauge invariance itself. And a massless particle, as we have gently established, must travel at c, always, without exception. Gauge invariance requires massless photons. Massless photons must travel at c, and so the speed of light is not just a consequence of physics. It is a consequence of the symmetry that makes physics possible. Breathe in, slowly, and out, deep in the mathematics of quantum field theory. There is a realm called momentum space, a place where physicists describe particles, not by where they are, but by how they are moving, by their momentum, their energy, their quantum numbers. In this realm, the behavior of quantum amplitudes, the mathematical quantities that determine how likely different processes are, must satisfy a property called analyticity. Analyticity is a smoothness condition, a requirement that these mathematical functions behave well, that they do not have unexpected singularities, unexpected breakdowns in the wrong places. In the boundaries of this analyticity, the edges of the region where the mathematics remains well behaved are set by c. When physicists try to extend these functions beyond the light cone into regions that would correspond to faster than light propagation, the analyticity breaks down. The mathematics develops singularities, infinities that cannot be tamed, breakdowns that cannot be repaired. The universe's own mathematics refuses to extend beyond c, like a map that ends at the edge of the known world. Beyond here, the equations simply stop making sense. Let that image sit with you gently. A map of reality, drawn in mathematics, ending precisely at the speed of light. Renormalization. This is a word that sounds technical, and it is. But the idea behind it is quietly fascinating. When physicists calculate things in quantum field theory, they often encounter infinities, intermediate steps in calculations that produce infinite answers, loops of virtual particles, contributing infinitely to certain quantities. Renormalization is a systematic procedure for handling these infinities, for reorganizing the mathematics, so that the infinite parts cancel, or are absorbed into physical parameters, leaving finite, measurable, meaningful predictions. It requires extraordinary care, and it only works when the theory is Lorentz invariant. when c is respected throughout. If you try to renormalize a theory that violates the speed of light, the infinities refuse to cancel. The procedure breaks down. The theory becomes unpredictable, unmeasurable, useless. Renormalization is another way in which the consistency of the universe depends on c, another thread in the vast web of mathematical requirements that the speed of light holds together. Rest now. Let your mind be quiet. The CPT theorem in the mathematics of quantum field theory. There is a deep and beautiful result called the CPT theorem. C stands for charge conjugation, the operation of replacing every particle with its antiparticle. P stands for parity, the operation of reflecting space, as if in a mirror. T stands for time reversal, the operation of running time backwards. The CPT theorem states that any consistent quantum field theory that respects Lorentz invariance must be invariant under the combined operation of all three, C, P, and T, together. This has profound consequences. It means that a particle moving forward in time is mathematically equivalent to its antiparticle moving backward in time in a mirror universe. It means that matter and antimatter behave in deeply symmetric ways when space and time are reflected together. And it means that the stability of this theorem, the protection it offers to the consistency of physics, depends entirely on Lorentz invariance, on the invariance of the speed of light. Violate C, and the CPT theorem fails. And if the CPT theorem fails, the relationship between matter and antimatter becomes unstable, unpredictable, potentially catastrophic. The speed of light protects not just causality, not just consistency, but the symmetry between matter and its opposite, between the universe and its mirror image. There is something quietly extraordinary about that. The same constant that limits how fast you can travel also holds together the deepest symmetries of particle physics. Breathe slowly. In the mathematics of quantum field theory, there is a technique called Wick rotation. It is a mathematical trick, a transformation that converts a description of physics in real time into a description in imaginary time. Imaginary time sounds like something from a dream, and in a way, it is. It is a mathematical landscape where time behaves like a dimension of space, where calculations become easier, more tractable, more beautiful. Physicists use Wick rotation extensively to calculate properties of quantum fields, to understand the behavior of particles, to study the structure of the vacuum. And the Wick rotation has a boundary. a limit beyond which the transformation cannot be safely performed. That boundary is defined by c. Beyond the light cone, the Wick rotation breaks down. The transformation produces inconsistencies, mathematical pathologies, things that cannot be interpreted physically, sensibly. Once again, the mathematics itself draws the line at C. And finally, something that sits at the very frontier of modern theoretical physics: asymptotic safety. One of the great unsolved problems in physics is how to reconcile quantum mechanics, the theory of the very small, with general relativity, the theory of gravity and spacetime. These two great frameworks do not fit together easily. When physicists try to combine them, infinities appear that resist renormalization, that cannot be tamed by the usual methods. One approach to solving this problem is called asymptotic safety. The idea, proposed by Steven Weinberg in the 1970s, is that gravity might have a special fixed point in the mathematical space of theories, a point toward which the theory flows as you probe it at higher and higher energies. At this fixed point, the theory becomes safe. The infinities become manageable. The predictions become meaningful. And the investigations of asymptotic safety consistently find that the speed of light remains a fixed and fundamental parameter. Even at this extreme limit, even at the boundary between quantum mechanics and gravity, even at the frontier of our understanding, C does not waver, does not soften, does not negotiate. The speed of light appears to be asymptotically safe itself, a constant that remains meaningful all the way to the edges of physics, all the way to the limits of our knowledge, and perhaps beyond. Let that thought drift through you like the last light of evening, slow and golden, and fading gently into dark. We have been somewhere unusual tonight, inside the mathematics of reality, walking the corridors of symmetry groups, and wave equations, and renormalization, and CPT theorems. And everywhere we looked, the same number appeared: c, the speed of light, constant, invariant, fundamental, protected, woven into every layer of the universe, from the largest structures of spacetime to the smallest fluctuations of quantum fields. It is not one fact among many. It is the thread that runs through all the facts, the number the universe returns to again and again, no matter where you look, no matter how deep you go. And you, resting here, breathing slowly, drifting towards sleep, are part of that universe, made of fields that obey Lorentz invariance. built of particles that interact through gauge bosons, held together by forces mediated at the speed of light. You are not separate from this mathematics. You are an expression of it. A local, temporary, beautiful expression of a universe that is consistent and symmetric and luminous all the way down. Let your thoughts grow soft now. Let the equations dissolve into something quieter, into the simple feeling of being here, of breathing, of resting inside a universe that knows what it is doing. Sleep, if you are ready. The mathematics will continue, holding everything in place, exactly as it always has, quietly, precisely, and without any need of your attention. Rest now. You are held completely in the speed of light. We'll keep watch. Still here. Still with you. Let the quiet find you. Wherever you are. Take a slow breath in and release it. Without hurry. We have spent time together in the deep mathematics of the universe, in the symmetries and structures that make reality coherent. And now, we come back, gently, to the world of experiment, the world of clocks and mirrors, of spinning rings and moving trains, of physicists who asked quiet questions, and let the universe answer. Because the beauty of physics is not only in its mathematics, it is in the fact that the mathematics can be tested, checked against reality, held up to the light, and found to be true. Every idea we have explored together, every symmetry, every equation, every quiet claim about the nature of spacetime has been confirmed by real experiments, run by real people, with real instruments, in real laboratories, and in the real world beyond them. Let us walk through some of those experiments tonight. Slowly, gently, one by one. The speed of light has been measured with extraordinary precision, many times, by many different methods, across more than 3 centuries of science. The earliest measurements were rough, but still remarkable. In 1676, the Danish astronomer Ole Romer noticed that the moons of Jupiter appeared to move slightly faster or slower, depending on where Earth was in its orbit. He realized, with quiet brilliance, that this was not the moon speeding up or slowing down. It was the light taking longer or shorter to cross the changing distance between Jupiter and Earth. From this, he estimated the speed of light. His number was not perfectly accurate, but it was in the right region, and it was the first real experimental evidence that light travels at a finite speed, that it takes time to cross space. Since then, the measurement has been refined, again and again, each time more precisely, each time confirming the same number: 299,792,458 meters per second. In a vacuum. Always. In 1983, the speed of light was incorporated into the very definition of the meter. The meter is now defined as the distance light travels in a vacuum in exactly 1,299,792,458th of a second. This is not a circular definition. It is a statement of confidence. The speed of light is so well established, so precisely known, so invariant, that we have made it a cornerstone of how we measure distance itself. C is no longer just a measurement. It is a definition, a foundation, a fixed point in the landscape of human knowledge. Let that feel like something solid. Now, a thought experiment that became an insight. One of the most elegant ways to understand time dilation is through something called a photon clock. Imagine a clock built from two mirrors facing each other, with a single photon bouncing back and forth between them. Each bounce is one tick. This clock keeps time by the speed of light, by c, precisely and unavoidably. Now imagine this clock is placed aboard a moving spaceship. From outside the ship, from the perspective of a stationary observer, the photon does not simply bounce straight up and down. It traces a diagonal path, because the clock is moving sideways as the photon travels. But the photon still moves at c. It cannot move faster. And so the diagonal path, which is longer than the straight vertical path, takes more time to complete. From outside the ship, the clock ticks more slowly. Not because anything is wrong with the clock, not because the photon is tired, but because the geometry of the situation demands it. The speed of light is fixed, and so time must bend instead. The photon clock is not a real device, but it demonstrates something utterly real. Time dilation is not a trick. It is a geometric consequence of the constancy of c. Inescapable and quietly beautiful. Let that image drift with you. Two mirrors, a single photon, and the bending of time itself. In the late 19th century, two American physicists, Albert Michelson and Edward Morley, set out to detect something called the luminiferous ether. At the time, many scientists believed that light, like sound, must travel through some medium. Sound travels through air. So light, they reasoned, must travel through something, an invisible, all-pervading substance they called the ether. If the ether existed, then Earth moving through it would experience a kind of ether wind, and light traveling with or against that wind would move at slightly different speeds. in different directions. Michelson and Morley built an extraordinarily sensitive instrument, called an interferometer, to detect exactly this difference. They found nothing. No difference. No ether wind. No variation in the speed of light. In any direction. At any time of year. This was one of the most important null results in the history of science. A null result is when an experiment finds nothing, when it expected to find something, and finding nothing, in this case, was everything. It told the world, quietly and firmly, that light does not need a medium, that its speed does not depend on direction, or on the motion of Earth through space. That C is the same, in every direction, for every observer. This null result became one of the foundations upon which Einstein built special relativity. A beautiful experiment that found nothing and changed everything. Breathe slowly. Now something that might seem at first like a contradiction. In certain materials, it is possible for particles to travel faster than light. Does in that material, when this happens, something remarkable occurs. A cone of blue light, spreading outward, like the optical equivalent of a sonic boom. This is called Cherenkov radiation, named for the Soviet physicist Pavel Cherenkov, who first observed and described it in the 1930s. It is real. It is measurable. It is beautiful to observe. That eerie blue glow in the water surrounding nuclear reactors is Cherenkov radiation. Particles moving through the water, faster than light moves through the water. But, and this is the gentle but essential point, they are not moving faster than c. The speed of light in water is significantly less than the speed of light in a vacuum. Light slows down in materials as it interacts with the atoms it passes through. The particles are faster than the slowed light, but still slower than c. Still slower than light in a vacuum. Still on the right side of the absolute limit. Cherenkov radiation is not a violation of the cosmic speed limit. It is a reminder that the true limit, the invariant limit, is the speed of light in vacuum, in the pure and empty geometry of spacetime, where nothing slows it down. That limit remains unbroken. Even here, even in the glow of reactor pools, even in the blue light of particles racing through water. Something similar is worth mentioning gently here. In certain circumstances, something called the phase velocity of light can appear to exceed c. The phase velocity is the speed at which the peaks of a wave move through space, and in certain media, certain optical arrangements, these peaks can indeed appear to move faster than c. But phase velocity does not carry information. It does not carry energy. It does not carry signals. It is a mathematical feature of the wave pattern, not a physical carrier of anything real. The group velocity, the speed at which the wave's energy actually travels, the speed at which a signal can be sent, never exceeds c. The universe is subtle here. It allows the appearance of faster-than-light motion in certain wave phenomena, while ensuring that nothing real, nothing that could carry a message, or a cause, or an effect, ever crosses the line. The universe is careful, patient, and precise. It closes every loophole, quietly and completely. Breathe in, gently. In particle accelerators, physicists push electrons and protons and other charged particles to extraordinary speeds, close to c, sometimes extraordinarily close. And as these particles accelerate, they radiate. They emit light, electromagnetic radiation. This is called synchrotron radiation, named for the type of accelerator in which it was first systematically studied. Synchrotron radiation is not just an interesting side effect. It is a confirmation. Every time a charged particle accelerates, it loses energy to radiation. And as it approaches c, that energy loss increases dramatically. The particle can never quite reach c, because as it gets closer, more and more of the energy pumped into it is radiated away as light, rather than converted into speed. The universe takes the energy and turns it into photons, rather than let the particle reach the forbidden speed. It is as though the universe has a release valve, a mechanism that bleeds off energy as light to prevent any massive particle from ever quite arriving at c. Synchrotron radiation is observed every day in accelerators around the world. It is so reliable, so well understood, that it is now used deliberately as a source of intense X-rays for scientific and medical research. The universe's speed limit has become a tool. Let that feel like something quietly wonderful. Now, one of the most elegant experimental confirmations of the constancy of c, the Sagnac interferometer. In 1913, the French physicist Georges Sagnac built a device that split a beam of light and sent the two halves around a loop in opposite directions. When the device was stationary, the two beams returned together in perfect step. No difference. When the device was rotated, a small but precise difference appeared. The beam traveling in the direction of rotation took slightly longer to complete the loop than the beam traveling against it. This is now called the Sagnac effect, and it confirms, in a direct and measurable way, how light behaves in rotating reference frames. It is the principle behind modern laser gyroscopes, used in aircraft and ships and spacecraft to detect rotation with extraordinary precision. Every time a pilot checks their orientation, every time a spacecraft corrects its attitude, the Sagnac effect and the constancy of C that underlies it is quietly at work. The speed of light, keeping people safe in the dark of the sky. In 1960, a German physicist named Rudolf Musbauer was awarded the Nobel Prize for discovering what is now called the Musbauer effect, a way of emitting and absorbing gamma rays with extraordinary precision. Shortly afterward, this effect was used in an elegant and careful experiment. A radioactive source was placed on a rotating disk, and its gamma rays were detected at different points on the disk. As the disk rotated, the source moved at different speeds relative to the detector, and the frequency of the gamma rays shifted in a way that matched precisely the predictions of special relativity. The time dilation was there, measurable, exact, matching the equations that have C at their center, a spinning disk, some gamma rays, and the quiet confirmation of one of the strangest predictions in all of physics. Breathe slowly now. In 1971, two physicists named Joseph Haffel and Richard Keating did something beautifully simple and profoundly important. They took 4 cesium atomic clocks, extraordinarily precise timepieces, accurate to billionths of a second, and they flew them around the world on commercial aircraft. When the traveling clocks returned and were compared with reference clocks that had remained on the ground, they disagreed. Not by much, by a tiny fraction of a microsecond. But the disagreement was exactly what the equations of special and general relativity predicted, accounting for both the speed of the aircraft and the difference in gravitational strength at altitude. Time had passed differently for the clocks that moved, just as Einstein said it would, just as the equations demand, just as the constancy of C and the geometry of spacetime require. This was not a theoretical result. It was real clocks, on real planes, flying real routes, around the real Earth. And the universe got the answer right, to the billionth of a second. Let that rest with you, like something deeply reassuring. The equations work. The universe is honest. And the clocks that disagree, by billionths of a second, confirm what has always been true. Time is personal, and the speed of light is the reason why. And finally, something that reaches beyond light itself, into the geometry of spacetime and the nature of gravity. Gravity, as Einstein described it, is not a force in the traditional sense. It is a curvature of spacetime. Massive objects bend the fabric of the universe, and other objects follow the curves. But gravity is not instantaneous. If the sun were to suddenly vanish, Earth would not immediately fly off in a straight line. It would continue orbiting for approximately 8 minutes, the time it takes for the change in gravity to travel from the sun to Earth. At the speed of light, gravity propagates at c. This was a prediction of general relativity, and in 2015, it was confirmed in one of the most extraordinary scientific moments in human history. Two massive black holes, spiraling toward each other across more than 1 billion light-years of space, merged in a fraction of a second, releasing more energy than all the stars in the visible universe combined. In the ripple in spacetime that this merger produced, a gravitational wave traveled outward in all directions at the speed of light for over 1 billion years. It crossed the universe, stretching and squeezing spacetime by an amount smaller than the width of a proton. In detectors on Earth, called LIGO, felt it. The gravitational wave confirmed that gravity travels at c, that the carrier of gravity, the graviton, if it exists, must be massless, must travel at the speed of light, must obey the same cosmic limit that governs photons and all other massless things. Gravity itself is bounded by c. Even the curvature of spacetime travels no faster than light. The universe has one speed for everything that reaches across it, one limit for every influence, every signal, every ripple, every wave. C. Always C. Let your breathing slow now. Very slowly. We have walked through laboratories tonight, through rotating disks and flying clocks, through interferometers and reactor pools, through the collision of black holes 1 billion light-years away. And everywhere we looked, the same answer waited. Patient. Unchanged. Confirmed. The speed of light is real. It is not just mathematical, not just theoretical, not just elegant. It is measured, checked, tested, confirmed by real human beings, with real instruments, asking real questions of a real and honest universe. In the universe, every single time gives the same answer. See? Let that feel like something you can trust. Let it settle into you. Like warmth, like certainty, like the slow and reliable turning of the earth beneath you. As you rest, there is more to come. More quiet truths, more gentle facts, drifting through the dark toward you, like light from distant stars. patient, and always arriving at exactly the right speed. Sleep now, if you are ready. The experiments are done for the night. The clocks are at rest. The photons are still traveling, as they always have, and always will, at sea, and nothing more. Rest. You are held in a universe that tells the truth. Still here, still with you. Let the stillness find you, wherever you have settled tonight. Take a breath, slow and deep, and let it go. Without effort. We have tested the speed of light in laboratories, in aircraft, in particle accelerators, in the quiet detection of gravitational waves from black holes a billion light years away. Tonight, we begin with something more intimate, something hidden in the behavior of the smallest particles we know, before we expand outward, all the way to the edge of the cosmos itself. The universe whispers see, at every scale, from the smallest quantum fluctuation to the largest structure in existence. Let us listen. We have spoken of c as a speed, as a limit, as a constant woven into the mathematics of space-time. But there is another way to think about it. A quieter way. A more fundamental way. C is the ceiling on how fast any signal, any physical influence, any change in the state of one thing can be communicated to another. This is called the signal propagation ceiling, and it is perhaps the most operationally important meaning of C. When you turn on a light, the photons travel outward at C. When two charged particles interact, the electromagnetic influence between them propagates at C. When a gravitational field changes, because a massive object has moved, that change ripples outward at C. Nothing learns about a change faster than C allows. Think about what this means. For the universe as a whole, there are regions of space so distant from us that light from there has not yet had time to reach us. Since the beginning of the universe, these regions exist. We believe they do, but we cannot see them. We cannot know what is happening there. Right now, we cannot receive their signals. They cannot receive ours. The signal propagation ceiling means that the universe is partitioned into causally connected regions and causally disconnected ones. Bubbles of knowability, separated by the absolute ceiling of C. Our observable universe, the sphere of space from which light has had time to reach us, is enormous, stretching billions of light years in every direction. And yet, it is only a fraction of everything that exists. Beyond our horizon, the universe continues. Vast, silent, unreachable. Because C, no matter how long you wait, can only carry signals so far. Let that image rest with you. A sphere of light surrounding you. Everything reachable within it. Everything beyond it. Forever quiet. Now, something extraordinarily precise. The electron, one of the fundamental building blocks of matter, has a property called spin. And because it has spin and charge, it behaves like a tiny magnet. The strength of this magnetic behavior can be described by a number called the anomalous magnetic moment, usually written as G-2, divided by 2. This number has been measured with breathtaking precision to more than 10 significant figures. It is one of the most precisely measured quantities in all of science and quantum electrodynamics. The quantum field theory of light and electrons, built on Lorentz invariance, built on the constancy of C, predicts this number to the same extraordinary precision. The agreement between theory and experiment is astonishing. If you measured the distance from London to New York with this level of accuracy, your error would be smaller than the width of a human hair. This is not luck. This is not coincidence. This is what happens when the theoretical framework is correct, when C is truly invariant, when Lorentz symmetry is truly exact. The anomalous magnetic moment of the electron is a confirmation of C, hidden in the heart of the electron itself. Quiet, precise, and speaking the same truth that every other experiment speaks. Breathe slowly. And there is another, called the Lamb shift. In the 1940s, the American physicist Willis Lamb measured the energy levels of the hydrogen atom with extraordinary care. He found a tiny discrepancy between what classical quantum mechanics predicted and what he actually observed. A small shift in the energy of certain electron states that should not have been there. This discrepancy, the Lamb shift, turned out to be a consequence of the quantum vacuum, that seething sea of virtual particles that flicker in and out of existence, even in apparently empty space. To calculate the Lamb shift correctly, you need quantum electrodynamics. You need Lorentz invariance. You need C. Precisely. Exactly. Woven into the calculation. And when you use the correct theory, when you respect C throughout, the prediction matches the measurement perfectly. The hydrogen atom, the simplest atom in existence, is a test of C. Every time an electron sits in its orbital, every time a photon is absorbed or emitted, the constancy of the speed of light is quietly confirmed. Again and again. These are not exotic experiments done in extreme conditions. They are the mundane operations of the most ordinary matter in the universe. Hydrogen, the most abundant element in existence, constantly confirming, in the quietest possible way, that C is what we think it is. Let that feel like something grounding. The universe confirming its own constants. In every atom. In every moment. Everywhere. And now something more subtle. And more profound. The fine structure constant is one of the fundamental numbers of physics, usually written as the Greek letter alpha. It describes the strength of the electromagnetic force, how strongly charged particles interact with light, with each other. It has a value of approximately 1/137, a pure number, with no units, no meters or seconds attached to it. Just a number. And it contains C within it. C is one of the quantities from which the fine structure constant is assembled, along with the charge of the electron and Planck's constant. Now here is something quietly extraordinary. Scientists have looked at light from distant quasars, ancient beacons at the edges of the observable universe. Their light has traveled for billions of years to reach us, carrying within it the signature of atomic transitions that occurred when the universe was young. And they have asked, was the fine structure constant the same back then as it is today? Did C and the other fundamental constants hold steady across billions of years, across the entire history of the observable universe? The answer, as best as we can determine, is yes. The fine structure constant does not appear to have changed. Not measurably. Not significantly. C has been what it is for as long as we can see, for as far back as the universe allows us to look. The speed of light is not just constant in space. It appears to be constant in time, unchanging across the entire history of the cosmos. Stable, patient, enduring. Let that sink in like something vast. And still, the same C that governs the photons reaching your eyes right now govern the first light that ever crossed the young universe billions of years ago, in a cosmos unimaginably different from the one we inhabit. The same number, waiting, consistent, and quiet. Now, let us expand outward, far beyond laboratories, far beyond atoms and electrons, into the realm of black holes, and gravity, and the deep structure of the cosmos. We have spoken of gravity, and how it propagates at sea. But gravity has another deep connection to the speed of light. In general relativity, gravity is described as curvature of spacetime. And this curvature, like all physical influences, propagates at sea. But more than that, the mathematics of general relativity is constructed in a way that is deeply analogous to the mathematics of electromagnetism. Both are field theories, Both respect Lorentz invariance. Both have their influences propagate at sea. Both are governed by wave equations, whose solutions travel at sea. Gravitational waves and electromagnetic waves are in many ways mathematical cousins, separated by the nature of what they describe, but united by the speed at which they travel. C is not just the speed of light. It is the speed of gravity, the speed of causality, the speed of the universe itself. And nowhere is this more vivid, more dramatic, more absolute than at the event horizon of a black hole. A black hole forms when matter is compressed into a region so small, so dense, that the curvature of spacetime becomes extreme, overwhelming, absolute, at a certain distance from the center, called the Schwarzschild radius. The curvature becomes so severe that not even light can escape this boundary. The event horizon is defined precisely by C. Inside the horizon, escape would require traveling faster than light. And since nothing can travel faster than light, nothing escapes. Not matter, not energy, not information, not light itself. The event horizon is C, made into a boundary, made into a wall, made into the edge of the known. Everything that crosses it is gone, not destroyed, not necessarily, but gone from our universe, unreachable, beyond all possible signals, beyond all possible knowledge. The black hole event horizon is perhaps the most vivid expression in the entire physical universe of what it means for C to be absolute. Let that image settle. A sphere of darkness, surrounded by a boundary, where the speed of light is exactly, precisely, just barely, not enough. And the formation of that horizon is itself governed by C. As matter collapses, as a dying star falls inward, under its own gravity, the event horizon does not appear all at once. It forms gradually, as the curvature of spacetime deepens, and the radius at which escape would require faster than light travel moves outward through the collapsing material. The horizon forms and propagates at a rate determined by C. And once formed, it is held in place by the absolute nature of that limit forever. There is another effect near black holes that speaks quietly of C. Massive rotating objects drag spacetime around with them as they spin, like a finger drawn slowly through a bowl of honey, pulling the honey around it. This is called frame dragging. And near a rotating black hole, it can become extreme. Spacetime itself, swirling around the black hole, like water around a drain. And yet, even here, even in this extreme swirling of space-time, the speed of light remains the limit. Frame dragging can pull light into curved paths around the black hole. It can slow signals or redirect them, but it cannot accelerate anything beyond c. The swirling of space-time, powerful as it is, exotic as it is, extraordinary as it is, bends to the same rule as everything else. C holds even here. Breathe slowly now. In general relativity, the paths that light follows through curved spacetime are called null geodesics. Geodesic, from the same root as geodesy, the measurement of the earth. It simply means the straightest possible path through a curved space. Light always follows the straightest possible path through whatever spacetime it finds itself in. It curves around massive objects, not because gravity pulls it, but because the spacetime it travels through is itself curved, and the straightest path through curved space is itself curved. And these paths, these null geodesics, have a beautiful property. They connect events that are separated by a space-time interval of zero, the same zero we encountered earlier. The signature of light, the signature of c, even in the most extreme curved space-time. Near black holes, near neutron stars, in the early universe, when density was unimaginable, light still travels along null geodesics, still moves at c, locally, in its own neighborhood of spacetime, still marks the boundary between what can be connected and what cannot. Null geodesics are the skeleton of causality, the threads that define what can influence what, woven through the curved fabric of spacetime, at every point, in every era, at every scale. And finally, we arrive at the very edge of what physics currently knows. The Planck scale. There is a length so small it makes atoms look enormous, so small that at this scale, the very concepts of distance and time begin to lose their meaning. This is the Planck length, approximately 1.6 times 10 to the power of minus 35 meters. A number so small, it is almost beyond imagination. At this scale, quantum effects and gravitational effects become equally important. The smooth fabric of spacetime may give way to something else, something grainy, foamy, fundamentally discrete, something our current theories cannot fully describe. And here, at the very limit of our knowledge, at the frontier beyond which our equations may no longer apply, c appears again. The Planck length is defined using c, along with the gravitational constant, and Planck's constant. From quantum mechanics. It is built from C as one of its essential ingredients. And physicists believe that whatever theory eventually describes this deepest scale of reality, whatever framework unifies quantum mechanics and gravity into a single coherent picture, it will still contain C, still respect it, still be bounded by it. Because every approach that has been tried, every candidate theory, string theory, loop quantum gravity, causal set theory, every serious attempt to go beyond our current knowledge, preserves Lorentz invariance, preserves C as a fundamental constant, even at the Planck scale, even at the boundary of the knowable, even in the foam of spacetime itself. The speed of light appears to hold. Let that feel like something quietly magnificent. We have traveled far tonight. From the magnetic moment of an electron to the event horizon of a black hole. From the Lamb shift in hydrogen to the swirling of spacetime around spinning masses. From the fine structure constant, measured in the light of ancient quasars, to the Planck scale, where space and time themselves may dissolve into something new. And everywhere, C was there. The same number, the same limit, the same quiet constant, threading through every scale, every era, every corner of the cosmos, from the smallest thing to the largest, from the earliest moment to the present night. C endures, invariant, patient, absolute. Let your thoughts grow soft now. Let the vast scales we have visited gently recede back into the quiet dark. You do not need to hold any of this. Just let it pass through you, like light through still water, leaving only a faint and gentle glow. The universe is deep, and you have looked into it tonight, from the comfortable distance of wherever you are resting. And it is beautiful, and it is consistent, and it holds together, all the way from electrons to black holes, all the way from Planck length to cosmic horizon, held together by many things, but perhaps most simply, most quietly, most absolutely, by one number: C. Sleep now, if you are ready. There are more facts ahead, more gentle truths, more quiet journeys into the luminous and patient universe. But for tonight, let C carry you forward through time at exactly the right speed, into the deep and restful dark. Rest. You are held. Still here. Still with you. Let the quiet wrap around you, like something soft and dark and warm. Take a long breath in. Hold it gently, and let it go. Tonight, we begin somewhere vast, somewhere cosmic, and we end somewhere that might make you smile. even half asleep, even drifting. Because tonight, we visit the universe at its largest scales, its deepest structures, its most ancient light. And then, we visit the science fiction, the dreams, the clever ideas that people have proposed for bending or breaking the cosmic speed limit. And we will find, as we always do, that the universe is patient, and the universe is consistent, and the universe has already thought of everything. Settle in. Let your body become heavy. Let your breathing slow. And just listen. The universe contains an enormous amount of information. Everywhere you look, matter is arranged in particular ways. Particles have particular positions and momenta. Fields have particular values. Stars are in particular places. Galaxies are oriented in particular directions. All of this arrangement, all of this specificity, all of this difference between one configuration and another is information. And information, as we have gently established, is physical. It must be stored in something, carried by something, encoded in something real. And there is a limit to how much information can be stored in a given region of space. This limit is called the Beaconstein bound, after the physicist Jacob Beaconstein, who first derived it in the 1970s. The bound says that the maximum amount of information that can be contained within a sphere of given size is proportional to the surface area of that sphere, not its volume, its surface area. This is deeply strange and deeply beautiful, and it leads to something called the holographic principle, the idea that the universe may be, in some profound sense, a kind of hologram. All the information needed to describe a region of space, encoded on its boundary, and woven into this bound, into this entropy density cap, is C. C appears in the formula, linking the bound to the physical properties of the region, as it appears in almost every deep formula. In almost every deep result, the universe has a maximum information density. And that maximum, like so much else, is shaped by the speed of light. Let that rest with you. The universe cannot contain more information than C allows. Even in its fullness, even in its complexity, it is bounded by the same quiet constant that bounds everything else. Now, something that reaches even deeper into the structure of spacetime, into its shape, its history, its beginning, the Weyl curvature hypothesis. Spacetime can curve in different ways. When matter is present, it curves spacetime locally, around itself, creating the gravitational fields we experience. This local curvature is described by something called the Ricci tensor. But spacetime can also have a more global curvature, a curvature that is not tied to local matter. but describes the overall shape of spacetime, its tidal forces, its large-scale structure. This is described by something called the Weyl tensor. At the very beginning of the universe, near the Big Bang, the Weyl curvature appears to have been extraordinarily small, almost zero, despite the enormous density of matter and energy present at that moment. The physicist Roger Penrose proposed that this is not a coincidence, but a deep law of nature, a constraint on the initial conditions of the universe, that the Weyl curvature must begin small, allowing the universe to start in a low-entropy state, from which structure and complexity and eventually life can emerge, and embedded in the mathematical description of how the Weyl tensor evolves, of how curvature propagates through spacetime, is c. The speed at which curvature changes and ripples and evolves is c. The speed of gravity, the speed of gravitational waves, the speed of the universe reshaping itself. C governs not just the content of spacetime, but its very shape, its curvature, its geometry, its past and its future. Breathe slowly. In the mathematics of differential geometry, the framework that Einstein used to describe curved spacetime, every point in spacetime has something called a tangent plane, or more precisely, a tangent space. The tangent space at a point is the local, flat, infinitely small neighborhood of that point. It is the spacetime seen by an observer, right there, right then, in their immediate vicinity, and in every tangent space, at every point, in every curved spacetime, however extreme the curvature, however close to a black hole, however early in the universe, the local speed of light is c. This is called tangent plane invariance, and it is fundamental, even when spacetime is twisted and stretched and folded by extreme gravity. The local physics in the immediate neighborhood of any observer is always the same, always special relativity, always c. As the local speed limit. The universe may be curved on large scales, wildly, dramatically curved, near black holes, in the early universe, in regions of extreme density, but locally, at every point, for every observer, the speed of light is c. The laws are the same. The limit holds, no matter where you are in the universe. If you shine a torch, right there, right now, in your immediate surroundings, it travels at c. Always. Without exception. Let that feel like something universal. Something shared. A constant experience. Available to every observer. Everywhere. In the entire history of the cosmos. And now, something that arrived at our detectors from the very edge of time. The cosmic microwave background. In the early universe, everything was hot. Unimaginably hot. Dense beyond imagination. A plasma of particles and light. So energetic. So tightly packed. That light could not travel freely. It was absorbed and re-emitted. Constantly. Trapped in the dense fog of matter. Then, approximately 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons to combine with protons to form neutral hydrogen atoms for the first time. And in that moment, the fog lifted. Light was freed. It streamed outward in all directions, filling the universe. That light, ancient beyond comprehension, has been traveling ever since, for approximately 13.8 billion years. It has been stretched by the expansion of the universe, cooled by the same expansion, from the searing temperature of a young cosmos to a faint and gentle glow, just a few degrees above absolute zero. And we can detect it right now with the right instruments. We can see this ancient light arriving from every direction equally. A perfect, almost perfectly uniform bath of microwave radiation surrounding us from all sides. This is the cosmic microwave background, the oldest light we can observe, the first light that ever traveled freely through the universe. And it travels at sea, as it has for every one of those 13.8 billion years. Not slowing, not speeding up, not varying. See, always see the tiny variations in the cosmic microwave background, the slight differences in temperature from one part of the sky to another, encode the seeds of everything that exists today. Every galaxy, every star, every planet, every living thing originated in the tiny fluctuations visible in that ancient light, and the way those fluctuations propagated in the early universe. The way sound waves moved through the primordial plasma, the way structure grew, is described by equations that contain C at their heart. The pattern we see in the cosmic microwave background, the precise statistical distribution of its variations, is a snapshot of physics operating at sea. In the very earliest moments of the universe, you are looking at the speed of light, confirmed across 13.8 billion years of cosmic history. Every time you see an image of the cosmic microwave background, let that feel like something ancient and luminous and quietly overwhelming. And one more thing, before we turn to something a little more playful. Bose-Einstein correlations. When identical particles of the same type, are produced in high-energy collisions, in particle accelerators, They show correlations in their behavior that depend on how close together they are in space and time. These correlations, called Bose-Einstein correlations, after the physicists whose statistics govern them, carry information about the size and lifetime of the region in which the particles were produced, and the way these correlations fall off with distance. The precise mathematical shape of their dependence on separation in space and time reflects the underlying Lorentz invariance, reflects C, built into the quantum statistics of identical particles, even in the spray of particles produced in the most violent collisions that human technology can create. C is there, shaping the correlations, the statistics, the quantum behavior of every particle that emerges. The speed of light is not just in the background, it is in the fabric of how particles behave when they are identical, when they are quantum, when they interact at any scale, at any energy, in any collision, anywhere. Breathe in slowly and out. And now, something a little different, something that might bring a small smile even as you drift towards sleep. Let us talk about the attempts, the clever, creative, audacious attempts to find a way around the speed limit. The universe has a speed limit, and humans, being what we are, immediately began wondering if there might be a loophole. The first loophole people imagined were called tachyons. A tachyon is a hypothetical particle that does not travel slower than light and does not travel at the speed of light, but instead always travels faster than light. The idea is not entirely absurd. Mathematically, if you take the equations of special relativity and insert an imaginary rest mass, a mass whose square is negative, the equations do not immediately explode. They produce a particle that always moves faster than c, that can never slow down to c, just as ordinary matter can never speed up to c. Tachyons would be strange. Their energy would decrease as they sped up. They would travel backward in time. From certain perspectives, they would carry causality violations wherever they went, and physicists have looked for them carefully, thoroughly, in particle accelerators, in cosmic ray detectors, in the decayed products of radioactive materials. They have never been found. Not once. Not a single confirmed tachyon in all the history of particle physics, and beyond the experimental absence. There are deep theoretical reasons to doubt them. A tachyon in quantum field theory signals an instability, not a new particle, but a sign that the theory has been built around the wrong ground state, the wrong vacuum. When the Higgs field was first theorized, its mathematical description temporarily contained something that looked like a tachyon, an imaginary mass, pointing to an instability in the assumed vacuum. And the resolution was not to accept faster than light particles, but to allow the field to settle into its true ground state, the one in which the Higgs has its real mass, and the instability disappears. Tachyons, in modern physics, are not portals to faster than light travel. They are warning signs, flags that wave gently in the mathematics to say, look here, something is not quite right. Find the true vacuum and try again. Let that rest softly. But there is another idea, one that captured imaginations far beyond physics, one that entered science fiction and stayed there, one that sounds almost plausible, because in some mathematical sense, it almost is. The Alcubierre drive. In 1994, the Mexican physicist Miguel Alcubierre published a remarkable paper. He asked a simple and brilliant question: if you cannot travel faster than light locally, could you instead move spacetime itself around you? His idea was this: compress spacetime in front of a spacecraft, expand it behind, and the spacecraft itself, sitting inside a bubble of normal spacetime, would be carried along like a surfer on a wave, without ever locally exceeding c. The mathematics worked. In a certain sense, Alcubierre found solutions to Einstein's field equations that described exactly this kind of warp bubble. And locally, inside the bubble, the speed of light would still be the limit. The passengers would feel nothing unusual, but the warp bubble as a whole could move through space faster than light. In principle, this is genuinely clever, and it generated enormous excitement, both within physics and far beyond it. But then people looked more carefully, and the problems emerged quietly and comprehensively. The Alcubierre metric, as the solution is called, is mathematically valid, in the sense that it satisfies Einstein's equations, but it requires, to function, something called exotic matter, matter with negative energy density, matter that would need to exist in enormous quantities. Negative energy density is not entirely fictional. Tiny amounts appear in certain quantum situations. In the Casimir effect, between closely spaced metal plates. But the amount required for a practical Alcubierre drive is so vast, so many orders of magnitude beyond anything that has ever been observed, or that any known physics suggests could exist, that the proposal is, for now, and perhaps forever, physically unrealizable. And there are further problems. The stability of the warp bubble is deeply questionable. when physicists examine what happens to the quantum vacuum inside and around the Alcubierre bubble, they find that it tends to be unstable. Quantum effects build up at the edges of the bubble. Energy accumulates. Radiation is produced. And the bubble, rather than maintaining itself, tends to destroy itself and anything inside it. The warp bubble, it seems, is not merely difficult to create. It may be fundamentally self-defeating. A structure that, by its very nature, cannot hold together long enough to be useful. There is something almost poetic about that. The universe allowing the mathematics, while quietly ensuring that the physics falls apart. Breathe slowly. Related to the Alcubierre drive is the concept of a soliton. A soliton is a wave that maintains its shape as it travels, not dispersing, not spreading out, but holding itself together by a precise balance of effects. The Alcubierre bubble is in some ways a gravitational soliton, a self-contained structure moving through spacetime. For solitons to be physically real, in any reasonable theory, they generally require that the energy density of the field supporting them be positive. This is called the positive energy condition, or the soliton energy positivity requirement, and it is closely related to the stability of the solutions. For the Alcubierre drive, the energy conditions are violated. The exotic matter required has negative energy, and when energy conditions are violated, when the positivity requirements fail, the solutions become unstable. They develop pathologies. They allow time machines. They permit paradoxes. The mathematics signals very clearly that something is wrong. The universe protects itself through energy conditions, through stability requirements, through the demand that solitons be supported by positive energy. And in doing so, it closes yet another apparent loophole in the speed limit. Yet another clever attempt, met by a quiet, patient, comprehensive no. And here is perhaps the most important thing to understand about all of these ideas. The Alcubierre drive, if it could exist, would not violate the local speed limit. This is subtle and beautiful and worth sitting with for a moment. Everything we have said about C, all the time dilation, all the length contraction, all the Lorentz invariance, all the causal protection, applies locally, in the immediate neighborhood of any observer. Light moves at c. Massive objects move slower than c. Causality is preserved. What the Alcubierre metric attempts is not to violate local physics, but to use the global structure of spacetime to achieve something that looks like faster than light travel from the outside, while remaining locally consistent. The global arrangement of spacetime, the large-scale curvature, is not directly limited by c. Space itself can expand faster than c, and indeed it does. In the early universe, and in the regions beyond our cosmic horizon, where the expansion of space carries distant galaxies away from us, faster than light could ever travel between us. This is not a violation of the speed limit. It is the expansion of the canvas, not the motion of anything on it. The speed of light limits how fast things move through space, not how fast space itself can stretch. And so the Alcubierre idea, while almost certainly physically impossible, for all the reasons we have explored, was not even trying to violate C locally. It was trying to use the global behavior of spacetime as a kind of cosmic shortcut. The universe notes this distinction carefully, and while it closes the door firmly on the Alcubierre drive for practical reasons, it allows the distinction to stand. Local speed limit only. Let that feel like something quietly elegant. The universe has one rule, applied locally, everywhere, always. And that local rule, consistently applied everywhere, is enough to hold everything together, enough to preserve causality, enough to make the cosmos coherent. The speed of light does not need to be a global absolute. It is a local one, and a local absolute, applied everywhere, is the same as an absolute everywhere. Rest with that. We have come a long way tonight. From the entropy of information to the ancient glow of the cosmic microwave background. From Bose-Einstein correlations to hypothetical tachyons. From the mathematics of warp drives to the quiet and comprehensive reasons why none of it works. The universe is patient with our imagination. It allows the mathematics. It entertains the proposals. It lets us work through the equations and find the contradictions ourselves. And then, gently, firmly, it closes every door, not to disappoint us, not to limit us, but because the universe is consistent, and consistency requires that the speed limit hold locally, globally, always, everywhere. Let your thoughts soften now. Let the warp drives dissolve. Let the tachyons fade. Let the cosmic microwave background glow faintly, somewhere at the edge of your awareness. Ancient and quiet, and bathing you from all directions in the oldest light in the universe. You are surrounded by that light right now, as you rest, as you breathe, as you drift. The first light that ever traveled freely is still traveling, still arriving, still filling the universe with its ancient and gentle presence. At sea. Always. Sleep now. If you are ready. The universe is vast and patient and full of more quiet truths waiting for you. In the dark. Rest. You are held in a cosmos that has been glowing for 13.8 billion years and will be glowing still long after tonight has passed into tomorrow. Still here, still with you. Let the silence settle around you like something ancient and unhurried. Take a slow breath in and out. We are deep into the night now, deep into the facts, deep into the quiet strangeness of a universe that keeps revealing itself, one gentle truth at a time. Tonight, we begin with two unusual phenomena, things that sit at the edges of perception, at the boundaries of wave and light, and that seem, at first glance, to suggest that something is moving faster than it should. And then, we go somewhere deeper still, into the quantum world, where things are uncertain and strange, and where the speed of light finds yet more ways to hold. Let your body become heavy. Let your eyes remain closed. Let the words drift past you like light, patient, and at exactly the right speed. The Olson-Richardson effect. This is something subtle, something that lives in the behavior of waves, and in the particular way that certain optical phenomena can seem to exceed the speed of light. When a light source moves toward you, the light it emits is compressed. The waves pile up slightly, arriving more frequently. This is the Doppler effect, something you have experienced with sound. When a vehicle passes you, its pitch shifting as it approaches and recedes. In certain geometries, certain arrangements of moving sources and observers, the apparent motion of a light source, as seen from a particular vantage point, can seem to exceed c. The source appears to sweep across the sky faster than light. This is called supraluminal apparent motion, and it has been observed in jets of plasma ejected from the centers of galaxies, from quasars, from active galactic nuclei, vast streams of matter hurled outward at close to the speed of light and appearing from Earth to move faster than light across the sky. But this is an effect of geometry, of the angle at which we observe the jet, of the fact that the plasma is moving toward us almost as fast as the light it emits, so that successive signals arrive with less and less time between them, creating an illusion of extraordinary speed. No information travels faster than c. No matter, no signal, no cause. The jet itself moves slower than light. The light it emits moves at c. And the apparent motion is a projection, a shadow of geometry, cast across our field of view. The universe allows the appearance, while quietly ensuring that the reality remains within bounds. The Olson-Richardson effect and related superluminal apparent motions are reminders that the universe is three-dimensional, and that projection onto a two-dimensional sky can produce illusions that look like violations of the cosmic speed limit, while being, in every physical sense, perfectly compliant with it. Let that rest gently. Things are not always what they appear. The universe is geometrically subtle, and its rules, when examined carefully, are never actually broken. Only apparently, and only to the inattentive eye. Breathe slowly. Phase singularity vortices. Light is a wave, and like all waves, it has a phase, a rhythm, a sense of where it is in its oscillation at any given moment. In complex beams of light, structured light, light that has been carefully shaped, the phase can vary from point to point, and in certain arrangements, the phase can spiral around a central point, like water circling a drain. At the very center of this spiral, the phase becomes undefined. The wave has no single phase at the center. All phases meet there, simultaneously, and at that singular point, the intensity of the light is exactly zero. A dark thread running through the beam, like the eye of a tiny, luminous hurricane. These are called phase singularities, or optical vortices, and they are real. They have been observed, studied, and even used in optical systems, microscopy, communications. Now, here is the subtle thing. The position of the phase singularity, the location of that dark central thread, can move, and in certain circumstances, it can appear to move very quickly, even faster than c. But again, this is not a violation of the speed limit. The phase singularity is not a thing. In the physical sense, it is a point of mathematical absence, a location where the wave amplitude is zero, not a carrier of information, not a carrier of energy, not a particle, not a signal. Moving a point of darkness is not the same as moving something. You can sweep a spotlight across the moon faster than light, simply by rotating your wrist quickly enough. But you are not moving anything to the moon. You are moving a pattern, an absence, a geometrical feature. Phase singularity vortices can race through optical systems at apparent speeds exceeding c, and they carry nothing with them, nothing real, nothing causal, nothing that the universe needs to worry about. The speed limit remains intact, even here, in the swirling dark centers of structured light beams. Let that image drift through you. A spiral of light, with a thread of darkness at its heart, moving swiftly, carrying nothing. And now, deeper, into the quantum world, where the strangeness becomes philosophical. The uncertainty principle, formulated by Werner Heisenberg in 1927. The uncertainty principle states that there are pairs of physical properties that cannot both be precisely known at the same time. The most famous pair is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it is moving. And the more precisely you know its momentum, the less precisely you can know its location. This is not a limitation of measurement, not a technological shortcoming. It is a fundamental feature of reality. The particle does not simultaneously have a precise position and a precise momentum. It is genuinely, irreducibly uncertain. Now, what does this have to do with C? The uncertainty principle, when extended into the relativistic framework, when combined with special relativity, with Lorentz invariance, with the constancy of C, becomes even richer. In relativistic quantum mechanics, the uncertainty principle applies not just to position and momentum, but to energy and time as well. The more precisely the energy of a system is defined, the less precisely the moment at which it has that energy can be determined. And this energy-time uncertainty gives rise to the quantum vacuum fluctuations we have already mentioned. The virtual particles, the Casimir effect, the Lamb shift, all of these emerge from the marriage of the uncertainty principle with the relativistic framework, with C at its heart. And crucially, the uncertainty principle does not allow information to travel faster than light, even though quantum measurements produce results instantaneously, even though entangled particles seem to coordinate their states across arbitrary distances. No information, no usable signal can be extracted from this and transmitted faster than C. The uncertainty principle and C are not in tension. They are partners, working together to produce the rich, strange, precise quantum world we live in. Breathe in, slowly. Now something older and more haunting. The Dirac Sea. In the 1920s and 30s, the British physicist Paul Dirac was working on a relativistic equation for the electron, an equation that combined quantum mechanics with special relativity, with C, in a single elegant framework. He found such an equation. It is called the Dirac equation, and it was a triumph. It predicted the spin of the electron naturally. without being told to. It predicted antimatter before antimatter was discovered. But it also produced a puzzle. The equation had solutions with negative energy. An electron, according to the Dirac equation, could in principle have negative energy. And if it could, it would fall to lower and lower energies, without limit, releasing energy as it fell, forever. Dirac proposed a resolution that is strange and beautiful and worth lingering on. He proposed that all the negative energy states are already filled, that the vacuum, empty space, is actually a sea, an infinite sea of electrons, packed into every possible negative energy state. This is the Dirac Sea, an infinite invisible ocean of electrons with negative energy, filling all of space, beneath the level of what we can observe. And because all those states are filled, ordinary electrons cannot fall into them. The Pauli exclusion principle, which says that no two identical fermions can occupy the same quantum state, prevents it. The sea is full. There is no room. Now, what holds the Dirac Sea stable? What prevents this infinite ocean of negative energy electrons from doing something catastrophic? The answer is again Lorentz invariance. C. The relativistic framework. The stability of the Dirac Sea. The fact that it does not radiate, does not collapse, does not catastrophically rearrange itself, depends on the Lorentz symmetry of the equation that describes it. Violate Lorentz invariance. Allow signals faster than c, and the Dirac Sea becomes unstable. The negative energy electrons begin to transition. Energy is released without limit. The vacuum destabilizes. C. By holding Lorentz invariance in place, keeps the quantum vacuum, keeps the Dirac Sea, keeps the ground state of the universe stable. You are resting tonight on a stable vacuum, a stable ground state, an infinite invisible sea of electrons, held quiet and still by the constancy of the speed of light. Let that feel like something deeply foundational. Goldstone bosons. When a symmetry of a physical system is spontaneously broken, something beautiful happens. A new particle appears. A massless particle, called a Goldstone boson. Spontaneous symmetry breaking is everywhere in physics. It is how the Higgs mechanism works. It is how superconductors form. It is how magnets develop their magnetic fields. And Goldstone bosons, the massless particles that emerge from broken symmetries, must travel at sea. Not because we impose this, but because they are massless. And massless particles, as we have established so gently, so repeatedly, must always travel at sea, cannot travel at any other speed. have no rest frame, no stillness, no option but see. Goldstone bosons are a consequence of symmetry, and their speed is a consequence of their masslessness, and their masslessness is a consequence of the theorem that connects them to the broken symmetry. And all of this is Lorentz invariant. All of it contains C. All of it confirms in yet another way, from yet another angle, from yet another branch of physics, the same quiet truth. See. Always see. Breathe slowly now. Very slowly. The Casimir effect. Take two perfectly flat metal plates and place them extraordinarily close together. In a vacuum. In the absence of everything. Or as close to everything as you can arrange. Something happens. The plates are pushed together. By nothing. By the vacuum itself. This is the Casimir effect. And it arises because, even in a vacuum, even in empty space, quantum fields fluctuate. Virtual particles appear and vanish. The vacuum is not nothing. It is a seething, fluctuating, quantum something. But between the plates, only certain fluctuations are allowed. Only waves that fit between the plates can exist there. Waves that are too long are excluded. Outside the plates, all fluctuations are allowed. The full richness of the quantum vacuum presses in from outside, while between the plates, only a restricted set pushes outward, and the pressure from outside exceeds the pressure from within, and the plates are pushed gently, measurably, together. The Casimir effect has been measured. It is real. It is a direct observation of the quantum vacuum, of the zero-point energy, of the fluctuations that the uncertainty principle demands. And it is Lorentz invariant. The calculation of the Casimir force depends on the relativistic quantum field theory of the electromagnetic field, which contains C, which respects C, which is built on C. The force between two metal plates in an empty room is a confirmation of the speed of light. Let that feel like something wonderfully strange. The Aharonov-Bohm effect. In quantum mechanics, particles can be affected by fields, even in regions where the fields themselves are zero. This seems impossible. A particle in a region where there is no electric field, no magnetic field, nothing measurable, can still be affected by the potential, the mathematical quantity from which the field is derived, even when the field itself vanishes. This was predicted by Yakir Aharonov and David Bohm in 1959, and it was subsequently confirmed by experiment. The Aharonov-Bohm effect reveals something deep about the nature of quantum mechanics, about what is real and what is merely a mathematical convenience. And yet, even here, even in this strange non-local seeming effect, no information travels faster than c. The phase shifts that the Aharonov-Bohm effect produces can only be observed after particles are brought back together. Compared. The comparison requires physical proximity, or a signal traveling at c or slower between the two parts of the experiment. The effect is subtle. It is quantum. It feels like action at a distance, but it is not. Causality is preserved. C is preserved. The universe is, once again, careful. Let that drift past you, like something half understood, in the way that dreams half understand themselves. We spoke earlier of the holographic principle, the idea that the information content of a region of space is encoded on its boundary, on its surface area, rather than its volume. This is called the holographic bound, and it emerges from the combination of general relativity, quantum mechanics, thermodynamics, and the constancy of C. The bound was first derived by Jacob Bekenstein, studying the thermodynamics of black holes, and later developed by Stephen Hawking, Leonard Susskind, and many others. It tells us something extraordinary about the nature of space itself. If all the information in a region is encoded on its boundary, then in some sense, the three-dimensional world may be a kind of projection of a two-dimensional reality. This is not established. It is one of the deepest open questions in physics, but it is suggested strongly and consistently by the mathematics of black hole thermodynamics and by the ADS/CFT correspondence, a precise mathematical duality between a theory of gravity in a curved space and a quantum field theory on its boundary. And throughout all of this, C is present in the entropy formula, in the Hawking radiation calculation, in the boundary field theory, in the correspondence itself. The holographic nature of reality, if it is real, is written in the language of C. Like everything else, like always, breathe in gently. String theory, one of the most ambitious and most controversial frameworks in theoretical physics, attempts to describe all particles and forces as tiny vibrating strings of fundamental energy in a space with more dimensions than we can observe. In string theory, the extra dimensions, beyond the three of space and one of time, that we experience, are compactified, curled up, rolled into tiny shapes, so small that they are invisible to any experiment we have yet devised. And the way these extra dimensions are compactified, the shape of the tiny spaces they curl into, determines the physics we observe. The particles, the forces, the constants of nature, and in every consistent compactification, in every valid string theory vacuum, Lorentz invariance is preserved. C is preserved. The four-dimensional physics that emerges always respects the cosmic speed limit. String theory is not confirmed. It makes predictions that have not yet been tested, and some that may never be testable with current technology. But it is mathematically consistent, and in its consistency, it requires C. Every compactification, every vacuum, every version of the theory that does not produce mathematical nonsense preserves C. The speed of light is not put into string theory by hand. It emerges from the requirement that the theory be consistent, that it not produce anomalies, that it not violate unitarity, that it make mathematical sense, even in 10 or 11 dimensions, even in the exotic landscape of possible string theory vacua. C holds locally, always, without exception. And finally, something beautiful from the frontier of quantum gravity, the thermofield double. In certain approaches to understanding black holes and the quantum nature of spacetime, physicists use a construction called the thermofield double state. Imagine two copies of the same quantum system entangled with each other in a very particular way. The combined state of both systems has the property that if you look at only one of them, it appears to be in a thermal state, a hot, random, disordered state. But the two together are in a pure quantum state, perfectly ordered, perfectly entangled. This construction, the thermofield double, is related to the geometry of black holes. In the AD/CFT correspondence, the thermofield double state corresponds to a spacetime geometry containing two black holes connected by a wormhole. A wormhole, a tunnel through spacetime, connecting two distant regions directly. This is, once again, the kind of thing that sounds like faster than light travel. A tunnel connecting two distant places directly. You enter here and emerge there, having crossed the space between in an instant. But the thermofield double wormhole is not traversable, not in any way that allows signals to pass through, not in any way that allows information to travel faster than c. The stability of the thermofield double state, the consistency of the construction, depends on Lorentz invariance, on C being preserved in both copies of the system, in both sides of the wormhole. And when physicists have explored whether information could somehow traverse the wormhole, whether a signal could take the shortcut, The answer, every time, is no. The wormhole is there, in the mathematics, beautiful and strange, but sealed to faster than light information by the same principle that seals everything else. See, patient, absolute, sealing every door that opens toward paradox. Let your thoughts grow very quiet now. We have been somewhere extraordinary tonight. Phase vortices and Dirac seas, Casimir plates and holographic bounds, string compactifications, and thermofield wormholes. And through all of it, C was there. In every equation, in every constraint, in every stability requirement, in every consistency condition. The universe is strange, and deep, and layered, with more structure than we can fully see. But it is consistent, and its consistency is everywhere, underwritten by one number, C. Let that feel like something you don't need to understand completely to feel the truth of. The way you don't need to understand how a river flows to know that it moves downhill. Always. The way you don't need to understand how sleep works to feel it coming. Now, slowly, let the quantum strangeness dissolve. Let the thermofield wormholes close. Let the Dirac sea grow still. Beneath you, you are resting on a stable vacuum, in a universe that knows what it is doing, held by constants that do not waver, by a speed that does not change, by a cosmos that is strange, and deep, and endlessly surprising, and yet, somehow, completely trustworthy. Sleep now, if you haven't already. The universe will continue, as it always does, quietly, at sea, and nothing more. Rest. You are held, still here, still with you, all the way to the end. Take one long, slow breath, in and out. We have traveled a long way together, through mathematics and experiments, through quantum fields and black holes, through warp drives and holographic bounds, through the very fabric of spacetime itself. And tonight, we arrive at the final stretch, the last gentle miles of this long and luminous journey. We begin with something that lives at the boundary between radiation and the changing geometry of space-time. And we end somewhere philosophical, somewhere quiet, somewhere that might change, very gently, how you think about the universe for the rest of your life. Let your body become completely still. Let your breathing find its slowest, most natural rhythm, and just receive the videometric. In general relativity, there is a family of solutions to Einstein's field equations. that describes spacetime. In the presence of radiation. Not static spacetime. Not empty spacetime. But spacetime that is actively receiving or emitting light. These solutions, discovered by the Indian physicist Prahlad Vaidya in 1951, describe a spacetime that changes as radiation flows through it. A black hole that grows as it absorbs infalling light, or a radiating star whose surrounding spacetime evolves as energy streams outward. And in these dynamic, changing, radiation-filled spacetimes, the speed of light remains c. Locally. Always. But here is what makes the Vaidya solutions particularly worth pausing on. They demonstrate that even in spacetimes that are actively changing, that are not static, not symmetric, not idealized, the causal structure, the light cones, the boundaries of what can influence what, are still governed by c. The event horizons that form in Vaidya spacetimes. As radiation pours in, and black holes grow, are defined by the same criterion as all event horizons, the surface beyond which escape would require exceeding c. Radiation falls in. Spacetime curves more deeply. The horizon grows. And throughout all of this dynamic change, c holds the causal structure in place, like a framework that bends and stretches, but never breaks. Even a universe in the act of changing itself, even spacetime actively reshaping around the flow of light, respects the limit of the light it contains. C governs not just static situations, but dynamic ones. Not just simple ones, but complex ones. Not just the idealized textbook universe, but the messy, changing, radiating, real one. Let that feel like something deeply reliable. And now, we begin the final ascent. The last 10 ideas. The deepest perspectives. The widest views. Conformal invariance. There is a special class of transformations in physics called conformal transformations. They are transformations that preserve angles, but not necessarily distances. They can stretch and squeeze spacetime, but they leave the local shape of things, the angles between curves, unchanged. A conformally invariant theory is one whose equations look the same after any conformal transformation. And theories of massless particles, theories where everything moves at c, are conformally invariant. Light itself, the electromagnetic field, is conformally invariant. Its equations, Maxwell's equations, do not change under conformal transformations. This is deeply connected to the fact that photons are massless, that they travel at c, that they have no rest frame, no sense of scale, no clock of their own. A conformally invariant theory lives at sea, because only at sea, only in the massless world, does the full conformal symmetry express itself. Conformal invariance is at the heart of some of the deepest results in theoretical physics. It appears in string theory, at the Planck scale, at critical points in phase transitions, in the ADS/CFT correspondence, in the study of quantum gravity, and everywhere it appears. It points back to C, to the massless, the scale-free, the conformally symmetric world of light. C is not just a speed. It is the natural home of conformal symmetry, the place where the universe looks the same at every scale. Let that feel like something spacious and still. We have spoken of the fine structure constant before. That dimensionless number, approximately 1/137, that describes the strength of electromagnetism. But let us look at it one more time, from a slightly different angle. The fine structure constant determines the spacing of spectral lines, the fine structure of atomic spectra, the subtle splitting of energy levels in atoms. That was first observed in the early 20th century. This splitting, this fine structure, arises because of relativistic effects. Because electrons in atoms move fast enough, that relativity, and therefore C, becomes important. The fine structure constant governs how strongly relativity affects atomic structure, how much C matters inside an atom, and it matters enormously. The chemistry of every element, the color of every flame, the spectrum of every star, the opacity of every gas cloud in space, all depend on the fine structure constant. All depend on C, built into the structure of matter. At the atomic level, C is not just a cosmic speed limit. It is an ingredient in the recipe for atoms, in the structure of matter itself, in the reason hydrogen glows red, and sodium glows yellow, and the sky is blue. The speed of light shapes the colors of the world. Let that rest with you, like something quietly beautiful. Dimensional analysis. This is a tool that physicists use, perhaps more than any other, to check whether equations make sense, to guess the form of answers before doing the full calculation, to understand the deep structure of physical relationships. The idea is simple. Every physical quantity has dimensions: length, time, mass, energy. And in any valid equation, the dimensions on the left must match the dimensions on the right. An equation that says a length equals a time cannot be correct. Not because we say so, but because it makes no sense. Now, Whenever you want to combine quantum mechanics with relativity, with gravity, the only quantities available to build a unit of length, a natural unit of time, a fundamental scale, are Planck's constant, the gravitational constant, and c. C is one of only three constants from which all other natural units can be constructed. It is dimensionally fundamental, not just fast, but foundational to the system of units in which the universe describes itself. Remove c from the universe, and you cannot even write down what a meter is, what a second is. In any natural, fundamental sense, c is not just a number in an equation. It is part of the language in which the universe is written. Breathe slowly. And now something that may seem obvious, but is actually profound. In Newtonian physics, the world we intuitively understand, the physics of everyday life, many particles can be described independently. Each particle has its position, its momentum, its energy, and the behavior of a collection of particles is just the sum of the individual behaviors. But in relativistic physics, in the world where c matters, everything changes. Even the kinematics of multiple particles, the way they interact, the way energy and momentum are conserved in collisions and decays, is fundamentally tied to c. When particles collide in an accelerator and new particles are produced, the conservation of relativistic energy and momentum, the rules that govern what can be created and what cannot, depend on c. The threshold energy for creating a new particle, the minimum collision energy needed to produce something new, is determined by Einstein's equation, E equals mc squared by c. At the heart of the calculation, every particle ever discovered, in every accelerator ever built, was found using collision energies, calculated from formulas that contain c. The Higgs boson, found at CERN in 2012, required collision energies predicted by equations built on c. C is not just a speed limit. It is the conversion factor between mass and energy, between rest and motion, between matter and the radiation. It can become, in every particle interaction, in every collision and decay, c is the silent accountant, keeping the books of energy and momentum perfectly balanced. Now, something that sounds simple, but reveals something deep. In everyday life, we believe in rigid bodies, objects that don't deform when you push them, that transmit force instantaneously from one end to the other. If you push one end of a perfectly rigid rod, the other end moves immediately, at the same instant, instantaneously, faster than any signal could travel. The But in a relativistic universe, perfectly rigid bodies cannot exist. When you push one end of a real rod, the atoms at that end are compressed. They push on the next layer of atoms, which push on the next, and so on, down the length of the rod. This compression, this mechanical signal, travels at the speed of sound in the material, which is always less than c. There is no material, no substance, no arrangement of matter, in which the speed of sound can reach c, let alone exceed it. Perfectly rigid bodies are forbidden by the speed of light, because a perfectly rigid body would transmit force instantaneously. An instantaneous transmission of force is a signal, and no signal can travel faster than c. The rigidity of everyday objects, the solidity of the chair, the floor, the walls, is an approximation, a convenient fiction that works at human scales and human speeds. But push deep enough, ask precisely enough, and the universe reminds you nothing is perfectly rigid, because C will not allow it. Let that feel like something quietly humbling. Even the ground beneath you is not perfectly solid. It only seems that way because you move so slowly through a universe that operates at sea. And now, a gentle return to where we began. We spoke early in our journey of the Lorentz group, the symmetry group of special relativity, the mathematical structure that contains all the transformations that leave the laws of physics unchanged, the full symmetry group of relativistic physics is called the Poincare group. It includes the Lorentz transformations, rotations and boosts, but also translations, shifts in space, and shifts in time. The Poincare group is the symmetry group of flat spacetime of the universe as it appears locally to any observer anywhere, and at the heart of the Poincare group, defining its structure, determining its character, is C. The group has a particular form because of C. Its representations, the mathematical objects that transform under it, correspond to particles with particular masses and spins. Every particle in the universe, every electron, every quark, every photon, every neutrino is classified by how it transforms under the Poincare group, by its mass and spin, by its relationship to C. The entire particle content of the universe, everything that exists, is organized by the symmetry group, whose defining parameter is the speed of light. We have come full circle from the first simple statement that C is invariant to this, the deepest symmetry of space-time, classifies all of existence, and C is its heartbeat. Breathe slowly. Now something philosophical. Something that reaches beyond physics. Into the question of why. In 1950, the physicist Enrico Fermi, sitting at lunch, asked a simple question. If the universe is vast and old and contains hundreds of billions of galaxies, each with hundreds of billions of stars, many with planets, where is everybody? This is the Fermi paradox, the puzzle of the great silence. If intelligent life is not extraordinarily rare, why have we detected no signals, no visitors, no evidence of anyone else out there? C is one of the quietest and most profound answers to this question. Even if the universe is full of civilizations, even if intelligence is common, the speed of light means that the universe is, for all practical purposes, impossibly large. A signal sent from the nearest star takes 4 years to arrive. From the center of our galaxy, 26,000 years. From the nearest large galaxy, 2.5 million years. Even a civilization that has existed for 1 million years longer than us could only have reached a tiny bubble of space, centered on their home, bounded by C, bounded by the signal propagation ceiling, bounded by the only speed the universe allows. C does not just limit how fast we can travel. It limits how fast we can know, how fast we can connect, how fast the universe can introduce one part of itself to another. Perhaps the universe is full of life, and the silence is simply the silence of distance, measured in light years, enforced by C. A cosmic quarantine, not of intention, but of physics. Every civilization, however advanced, however ancient, however wise, is bounded by the same horizon, the same light cone, the same speed. C is the great equalizer of the cosmos, the thing that makes the universe simultaneously full of possibility and full of loneliness. Let that rest somewhere deep. And now, stepping back, all the way back to the widest view, we have explored C from 100 angles, through symmetry and experiment, through quantum fields and black holes, through the mathematics of particles, and the philosophy of causality. And what emerges from all of these perspectives is a single, unified, quiet conclusion. C is not a property of the universe. It is the universe. In a certain sense, it is the rate at which space and time exchange themselves, the conversion factor between the dimensions of existence, the parameter that defines what spacetime is. Without C, there is no spacetime. There is no four-dimensional fabric. There is no causality. No conservation laws. No particles. No structure. No physics. Nothing. C is not a rule imposed on the universe from outside. It is not a speed limit posted on a sign by some cosmic authority. It is the geometry of existence itself, the architecture of reality, expressed as a number: 299,792,458 meters per second. And everything that exists, everything that has ever existed, everything that will ever exist, lives inside the structure that C defines. You, right now, are living inside that structure, breathing inside it, resting inside it, dreaming inside it. And finally, the last thought, the most important one, the one that changes, very quietly, how you might think about light for the rest of your life. We have called it the speed of light throughout this long and gentle journey, because that is its name. That is how we discovered it, by measuring how fast light travels, by timing a photon crossing a room, or bouncing off a mirror, or arriving from a distant moon of Jupiter. But that name is, in a sense, misleading. C is not the speed of light in any deep sense. Light travels at C because light is massless, and massless things must travel at the maximum speed that the geometry of spacetime allows. But C itself is not about light. C is the speed of causality. It is the speed at which causes produce effects. The speed at which the present becomes the future. The speed at which one thing can reach out and touch another across the fabric of space and time. Gravity travels at C, not because gravity is made of light, but because gravity is a causal influence, and all causal influences travel at C. Gravitational waves travel at C. Gluons, the carriers of the strong nuclear force, would travel at C if they were not confined within particles. The influence of a magnetic field, changing at one location, reaches another. At C, everything that can reach across space, everything that can carry a cause to an effect, does so at C. C is the speed at which the universe talks to itself. And light, beautiful, ancient, warm, familiar light, is simply one of the most common, most natural, most observable messengers, traveling at the only speed the universe allows for messages. When you see a star tonight, when you watch a candle flame, when light falls across your closed eyelids, you are not just seeing light. You are witnessing causality. In motion. The universe reaching out. From a source. To your eyes. At the only speed it knows how to use. See. The speed of causality. The speed of reality. The speed at which existence propagates itself through the darkness. And tonight, in this long and quiet darkness, you have traveled with it for a little while, through all its mathematics, all its experiments, all its philosophy, all its strangeness, all its beauty. And now, you can rest. Let the facts dissolve. Let the equations fade. Let the symmetries and the event horizons and the warp drives and the photon clocks gently, one by one, go quiet. What remains when everything else fades is this: you are here in a universe that makes sense, a universe that is consistent and logical and luminous, a universe where causes lead to effects, where time flows in one direction, where the ground is stable beneath you, where the same laws apply everywhere, for everyone, always, and holding all of that together, quietly, invisibly, patiently, is one number. See, not the speed of light, the speed of everything, the speed of the universe itself, becoming what it is, moment by moment by moment. Sleep now. You have traveled far enough. You have understood enough. You have listened and followed and wondered, and that is more than enough. Let sea carry you now, forward through time, at the only speed there is, into the deep, and the dark, and the warm, and the quiet. The universe will be here when you return, exactly as you left it, consistent, patient, and glowing, always glowing, at sea. Rest now. You are held. You are home. In the speed of light, will keep watch through the long and luminous night.